Welcome back. Tonight, we settle in with the gentle mathematics of gravitational balance, those peculiar regions in space where the pull of two massive bodies, a planet and its sun, a moon and its world, converge into something like stillness, quiet harbors amid the endless drift, where satellites and telescopes can linger without burning precious fuel, held in place by nothing more than the patient arithmetic of celestial mechanics, a kind of cosmic equilibrium that has fascinated astronomers for centuries. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the city of Turin, in the year 1736, a child was born into a family of Italian and French heritage, and his parents named him Giuseppe Lodovico Lagrange, though the world would come to know him by the French form of his name, Joseph Louis Lagrange, and it is under this name that his contributions to mathematics and celestial mechanics would be remembered for centuries to come. Turin at that time was part of the Kingdom of Sardinia, a place where Italian culture mingled with French influence, and the young Giuseppe grew up speaking both languages with equal fluency, a circumstance that would later ease his passage into the intellectual circles of Paris, though that journey lay many decades in the future, beyond experiences and discoveries that he could not yet imagine as a child learning his letters and numbers in the foothills of the Alps. His father had held a position of some importance as the treasurer of the Office of Public Works and Fortifications, and the family had once enjoyed comfortable prosperity, but through a series of unfortunate speculations, much of this wealth was lost during Lagrange's childhood, a reversal of fortune that he would later regard with something approaching gratitude, for he believed that had he inherited wealth, he might never have turned his attention so completely to mathematics, which became the great passion and occupation of his life. There is something quietly reassuring in this observation, the notion that what appears to be misfortune may sometimes redirect us toward the work we were meant to do. Though of course such reflections are easier to make in hindsight, when the shape of a life has become clear and its achievements can be measured against what might have been. As a young man, Lagrange initially intended to study law, following a path that his family considered respectable and practical, but his encounter with the works of Edmund Halley and Isaac Newton transformed his interests entirely, and by the age of 17 he had devoted himself completely to mathematics, teaching himself from books and corresponding with the great mathematicians of his day with a boldness that was remarkable for one so young and so far removed from the major centers of European learning. His talent was evident from his earliest papers, and by his late teens he was already making contributions that attracted the attention of established scholars, including the great Leonhard Euler, who was then perhaps the most prolific and influential mathematician in all of Europe. It was Euler who had first made progress on the ancient puzzle of how three bodies move through space when bound together by their mutual gravitational attraction, a problem that had troubled astronomers and mathematicians since Newton's time. For while the motion of two bodies orbiting each other could be described with elegant precision, the addition of a third body created complexities that seemed to defy complete solution. In 1750, Euler had identified three special points along the line connecting two large bodies, such as the Earth and the Moon, or the Sun and a planet, where a small third body might remain in a stable position relative to the other two, neither drifting toward one nor the other, but moving along with them as though fixed in place by invisible threads. These 3 points, which we now call L1, L2, and L3, were Euler's contribution to the problem, and they represented a significant advance in understanding, though Euler himself recognized that his solution was incomplete, that there might be other such points waiting to be discovered by someone with the mathematical skill to find them. Lagrange took up this challenge in the 1760s, corresponding with the French mathematician Jean-Le-Rond d'Alembert, who had become something of a mentor and advocate for the young Italian, recognizing his extraordinary abilities and encouraging his work on the most difficult problems of the age. D'Alembert was a complex figure, brilliant and sometimes prickly, but he saw in Lagrange a kindred spirit, a mathematician whose devotion to abstract reasoning matched his own, and their letters reveal a relationship of mutual respect and intellectual fellowship that sustained Lagrange through years of solitary work in Turin, far from the academies and salons of Paris, where scientific reputations were made and debated. In 1772, the Paris Academy of Sciences announced a prize competition on the subject of the moon's motion and its perturbations, a topic of both theoretical interest and practical importance, for accurate predictions of the moon's position were essential for navigation at sea, where sailors relied on lunar observations to determine their longitude and avoid the countless hazards of ocean voyages. Lagrange submitted his entry, a paper titled Essai sur le problème des trois corps, which translates as Essay on the Problem of Three Bodies, and in this work he presented not only his analysis of lunar motion but also his proof that there existed two additional points of equilibrium beyond the three that Euler had found, points that lay not along the line connecting the two main bodies, but at positions that formed equilateral triangles with them, so that if you were to draw lines connecting all three positions, including the two main bodies and either of the new equilibrium points, you would produce a triangle with all sides of equal length and all angles measuring precisely 60 degrees. This was a discovery of pure mathematics, arrived at through careful analysis and rigorous proof rather than through observation or experiment, for there was in 1772 no telescope powerful enough to detect any object that might occupy these positions, and indeed there was no particular reason to expect that any natural objects would be found there, the points being purely theoretical constructs arising from the equations of motion rather than features that anyone had noticed in the actual heavens. Lagrange himself seems to have regarded his discovery as a matter of mathematical interest rather than practical application, a contribution to the beautiful edifice of theoretical knowledge rather than a tool for navigators or astronomers, and in this he was not mistaken, for more than a century would pass before any celestial body was discovered occupying one of these special positions. The prize was awarded jointly to Lagrange and to Euler, who had also submitted an entry, a fitting recognition of the relationship between their work, for Lagrange had built upon Euler's earlier discoveries just as future mathematicians would build upon his own, the progress of science proceeding always through this accumulation of insights, each generation standing upon the shoulders of those who came before and reaching a little higher into the unknown. The Academy's recognition brought Lagrange increased fame and eventually led to an invitation to move to Berlin, where Frederick the Great was assembling a court of philosophers and scientists, and there Lagrange spent more than 20 years, continuing his mathematical work in the relative tranquility of the Prussian capital. His approach to the three-body problem employed what we now call the restricted three-body problem, a simplification that made the mathematics tractable by assuming that one of the three bodies was so small that its gravitational influence on the other two could be neglected entirely, so that it moved through a gravitational field created by the two larger bodies without itself affecting that field in any measurable way. This assumption, while not strictly true for any real objects, provides an excellent approximation for situations where the mass difference is extreme, such as a tiny asteroid moving under the gravitational influence of the Sun and Jupiter, or a spacecraft navigating between the Earth and the Moon, and it allowed Lagrange to find exact solutions where more general approaches yielded only approximations or numerical estimates. The 2 points that Lagrange discovered, which we now designate L4 and L5, possess a property that distinguishes them from the 3 collinear points that Euler had found. For while objects at L1, L2, and L3 occupy what might be described as precarious balance, requiring small corrections to remain in place over long periods, objects at L4 and L5 exhibit a peculiar kind of stability that keeps them in place even when slightly disturbed, provided certain conditions regarding the masses of the 2 main bodies are satisfied. This stability arises from the interplay of gravitational and rotational effects in a manner that Lagrange understood mathematically long before anyone had occasion to observe it in nature or to exploit it for practical purposes. After the death of Frederick the Great in 1786, Lagrange accepted an invitation to join the Academy of Sciences in Paris, where he had long been admired from afar, and he settled into a new life in the French capital just as the tremors of revolution were beginning to be felt throughout the kingdom. The years that followed were dangerous ones for men of learning, particularly those with connections to the aristocracy or the old regime, and many of Lagrange's colleagues fled the country or met tragic ends during the Terror. But Lagrange himself survived, perhaps because his quiet temperament and devotion to abstract mathematics rendered him harmless in the eyes of those who sought enemies of the revolution among the intellectual classes. There is a story, perhaps apocryphal but often repeated, that when the great chemist Antoine Lavoisier was sentenced to death by the Revolutionary Tribunal, an appeal was made on behalf of his scientific contributions, to which the judge reportedly replied that the Republic had no need of scientists, and Lavoisier was executed the following day. Lagrange, upon hearing this news, is said to have remarked that it took only a moment to cut off that head, but 100 years might not produce another like it, a comment that reveals both his grief at the loss of a friend and colleague, and his understanding of how rare and precious genuine scientific talent truly is. When Napoleon came to power, he expressed great admiration for Lagrange, appointing him to the Legion of Honor and later making him a Count of the Empire, distinctions that Lagrange accepted with his characteristic modesty, never having sought fame or position for their own sake, but only the quiet opportunity to pursue his mathematical investigations. Napoleon, who fancied himself something of a mathematician and who understood the practical applications of science for military and civil engineering purposes, enjoyed conversing with Lagrange on mathematical topics, though whether these conversations brought genuine pleasure to Lagrange or merely represented obligations to be endured with patience, the historical record does not clearly reveal. In his later years, Lagrange spoke of mathematics as a beautiful edifice, a structure built by generations of thinkers, each contributing their stones to a building that none would live to see completed. And this image captures something essential about his view of scientific work, as a collaborative and cumulative endeavor rather than a series of individual triumphs. He did not boast of his discoveries or seek priority disputes with other mathematicians, preferring always the contemplation of abstract problems to the contests of reputation and credit that sometimes disturbed the scientific community of his era. He died in Paris in 1813, at the age of 77, having lived through the tumultuous transformation of European society and having contributed foundational ideas to mathematics, mechanics, and astronomy that would influence generations of scientists yet to come. He never knew that the points bearing his name would one day be occupied by thousands of asteroids, nor that spacecraft from Earth would be stationed at these locations to observe the Sun or peer into the depths of the universe, nor that his purely theoretical discovery would become a practical necessity for the exploration of space. He had sought only to understand, to find the hidden order beneath the apparent complexity of celestial motions. And in this he succeeded beyond any measure he could have applied during his own lifetime. The 5 points that now bear the names of Lagrange and Euler, L1 through L5, represent one of those rare instances where pure mathematical reasoning revealed features of the physical universe that observation had not yet disclosed. Invisible places in space where the competing influences of gravity and motion combine to create pockets of relative calm. Cosmic parking spots, as it were, that exist whether or not anyone is there to occupy them, and that waited more than 100 years after their mathematical discovery to play any role in human affairs. And now, as we prepare to explore these points in greater detail, examining their properties and their uses and the objects that inhabit them, we may carry with us some appreciation for the quiet scholar who first proved their existence, working by candlelight in Turin and Berlin and Paris, manipulating equations that described a universe he could observe only with his mind, and leaving behind a gift that he could never have imagined anyone would need. In the year 1906, at the Heidelberg Observatory nestled in the gentle hills of southwestern Germany, an astronomer named Max Wolf was engaged in the patient and methodical work of examining photographic plates of the night sky, searching for the telltale streaks that would indicate the presence of previously unknown objects moving against the fixed backdrop of distant stars. Wolf had pioneered the use of astrophotography for discovering asteroids, a technique that allowed him to capture long exposures of particular regions of the heavens, and then carefully compare these plates to identify any points of light that had shifted position between observations. And on the night of February 22nd of that year, his careful examination revealed something rather remarkable. A faint object located not in the main asteroid belt between Mars and Jupiter where most such bodies were found, but rather at a considerable distance ahead of Jupiter in its orbit, occupying a position that corresponded almost precisely to the theoretical location known as the fourth Lagrange point. This discovery, which Wolf designated 588 Achilles after the legendary Greek hero of the Trojan War, represented the first confirmation that the gravitational peculiarities predicted by Joseph Louis Lagrange more than a century earlier could indeed serve as natural collection points for celestial debris, and the finding generated considerable interest among the astronomical community of the early 20th century, as it demonstrated that the mathematical elegance of Lagrange's equations translated into tangible, observable phenomena in our own solar system, where objects could remain suspended in these gravitational alcoves for millions upon millions of years, gently liberating around their equilibrium positions like leaves floating in a slowly turning eddy of a stream. The photographic plates that Wolf employed at Heidelberg represented a significant advancement over the visual observation techniques that had dominated asteroid hunting in previous decades, as the sensitive emulsions could accumulate light over extended exposure times and record objects far too faint for the human eye to perceive directly through a telescope eyepiece. And this method also had the considerable advantage of creating a permanent record that could be examined at leisure, compared with other plates, and studied by multiple astronomers, which contributed greatly to the reliability and reproducibility of discoveries during this productive era of astronomical research. Following Wolf's announcement, other astronomers began searching the same region of sky, and it was only a matter of weeks before another German astronomer, August Kopff, working at the same Heidelberg Observatory, identified a second object in an even more intriguing location, this one residing not at the L4 point ahead of Jupiter, but rather at the L5 point trailing some 60 degrees behind the giant planet in its orbit. Kopff named this new discovery 617 Patroclus, after the beloved companion of Achilles in the Greek epic tradition, and this finding demonstrated that both of the stable Lagrange points in the Sun-Jupiter system were capable of hosting such objects, a pair of gravitational refuges positioned symmetrically around the planet's orbital path like quiet harbors on either side of a great maritime route. The naming convention that emerged during these early years of Trojan asteroid discovery has a certain charming quality to it, as astronomers established the tradition of assigning names from the Greek side of the Trojan War to objects found at the L4 point, which leads Jupiter in its orbit, while reserving names from the Trojan side for objects discovered at the trailing L5 point. This convention, however, was not established until after the first few discoveries had already been named, which resulted in a delightful historical accident that astronomers have come to refer to with gentle humor, namely that Patroclus, a Greek hero, found himself catalogued among the Trojans at L5, while another early discovery, 624 Hector, named for the greatest of the Trojan warriors, was located at L4 among the Greeks. These two objects are therefore sometimes referred to as spies in the enemy camp, a whimsical designation that adds a touch of narrative color to what is otherwise the straightforward business of cataloging celestial bodies according to their orbital parameters. The positions occupied by these objects, 60 degrees ahead of and behind Jupiter as measured from the Sun, correspond precisely to the locations where Lagrange mathematics predicted that small bodies could achieve a stable equilibrium with the gravitational influences of both the Sun and the massive planet. At these points, an object orbits the Sun with precisely the same period as Jupiter, maintaining its relative position year after year, century after century, because the combined gravitational effects of our star and the giant planet create a gentle potential well from which there is little tendency to escape under normal circumstances. The objects do not remain perfectly stationary at these points, but rather oscillate slowly around them in complex patterns called tadpole orbits or horseshoe orbits, depending on their precise energy and angular momentum, though these librations occur over such extended timescales that for most practical purposes the asteroids can be considered permanent residents of their respective Lagrangian neighborhoods. In the decades following these initial discoveries, astronomers continued to identify additional objects at both the L4 and L5 points of Jupiter's orbit, and the catalogue grew steadily as telescope technology improved and systematic surveys became more comprehensive. By the middle of the 20th century, several dozen Jupiter Trojans were known, and by its end, improved detection methods had pushed this number into the hundreds. The advent of automated sky surveys in the 21st century, employing sensitive digital detectors and sophisticated software algorithms capable of identifying moving objects against the stellar background, has accelerated the pace of discovery dramatically. And as of recent counts, the known population of Jupiter Trojans exceeds 12,000 objects, with astronomers estimating that the total population larger than 1 kilometer in diameter may number in the hundreds of thousands, while even smaller bodies likely exist in quantities that defy easy enumeration. Among these thousands of known objects, some stand out for their considerable size, and the largest of the Jupiter Trojans, 624 Hector, the Trojan spy residing among the Greeks at L4, measures approximately 225 kilometers along its longest dimension, making it a substantial body by asteroid standards, though still far smaller than any of the major moons of the outer planets. Hector has an elongated, somewhat irregular shape that some astronomers describe as resembling a peanut or perhaps two objects in close contact, and it possesses a small moon of its own, discovered in 2006, which orbits the larger body at a distance of several hundred kilometers. Other notable Trojans include 617 Patroclus, which was found in 2001 to be a binary system consisting of two similarly sized objects orbiting their common center of mass, and 624 Hector's fellow L4 resident 911 Agamemnon, named after the king who led the Greek forces in the legendary conflict. The scientific interest in Jupiter's Trojans extends well beyond the simple cataloguing of their positions and sizes, as these objects are believed to represent some of the most primitive and unaltered material remaining from the early epochs of solar system formation, preserved in their gravitational refuges like specimens in a cosmic museum. Unlike asteroids in the main belt, which have been subjected to countless collisions and thermal processing over the eons, and unlike comets, which lose material each time they approach the Sun, the Trojans have resided in the cold, relatively stable outer regions of the solar system for billions of years, potentially retaining chemical and physical characteristics that date back to the protoplanetary disk from which all the planets formed. This scientific potential motivated the development and launch of NASA's Lucy mission, which lifted off from Cape Canaveral in October of 2021 on a 12-year journey designed to conduct close flybys of 7 different Trojan asteroids, an ambitious itinerary that will take the spacecraft on a complex trajectory involving multiple gravity assists from Earth. The mission, named after the famous Australopithecus fossil whose discovery revolutionized our understanding of human origins, aims to revolutionize our understanding of planetary origins by examining these primitive bodies up close, measuring their compositions, densities, surface features, and any satellites or rings they might possess. Lucy will visit objects in both the L4 and L5 swarms, providing comparative data that will help scientists understand whether the two populations share common characteristics or differ in significant ways. And the spacecraft's instruments are designed to detect the presence of organic compounds, water ice, and various mineral signatures that could illuminate the conditions prevailing in the early solar system. While Jupiter's Trojans are by far the most numerous and best studied, the same gravitational phenomenon that creates stable regions at the L4 and L5 points of Jupiter's orbit operates for other planets as well, though with varying effectiveness depending on the masses and orbital configurations involved. Neptune, the distant ice giant residing in the cold outer reaches of our planetary system, has been found to possess its own population of Trojan asteroids, with more than 30 such objects now confirmed to occupy the planet's L4 and L5 points. The first Neptune Trojan, designated 2001 QR322, was discovered in that year through systematic surveys of the outer solar system, and subsequent observations have revealed a population that, while much less thoroughly catalogued than Jupiter's, may actually be comparable in total number, as the extreme distance of these objects from Earth makes them exceptionally difficult to detect with current technology. Closer to the Sun, the smaller terrestrial planets have also been found to harbor Trojan companions, though in much smaller numbers. Mars possesses 9 confirmed Trojan asteroids, with the first, 5261 Eureka, discovered in 1990 at the planet's L5 point, and subsequent surveys have identified additional objects at both stable points. These Martian Trojans are considerably smaller than their Jovian counterparts, reflecting both the lower mass of Mars, which creates shallower gravitational wells at its Lagrange points, and the more dynamically active inner solar system, where orbital perturbations from the larger planets can destabilize such populations over geological timescales. Perhaps the most intriguing discovery in this regard concerns our own planet, as Earth was found to possess at least one Trojan asteroid, an object designated 2010 TK7, which was detected in October of 2010 by NASA's Wide Field Infrared Survey Explorer telescope, known as WISE. This asteroid, measuring approximately 300 meters in diameter, occupies a complex tadpole orbit around Earth's L4 point, oscillating above and below the plane of our orbit and tracing out an intricate three-dimensional path that keeps it perpetually ahead of our planet as both circle the Sun. The discovery of Earth's Trojan was particularly challenging because objects at our L4 and L5 points appear, from our perspective on Earth, to be located in the same general direction as the Sun, making them difficult to observe against the solar glare. And WISE's infrared capabilities, combined with its position in space above Earth's atmosphere, proved essential in identifying this elusive companion. The study of Trojan asteroids continues to yield insights into the architecture and history of our solar system, revealing the subtle gravitational structures that organize celestial material into persistent patterns and preserve ancient relics from the earliest chapters of planetary formation. These populations of asteroids, trapped in their respective Lagrange points like ships at anchor in cosmic harbors, remind us that the solar system is not merely a collection of planets orbiting independently around the Sun, but rather a complex, interconnected gravitational system in which the influences of multiple bodies combine to create regions of stability and instability, channels of migration and refuges of permanence, all governed by the same mathematical principles that Lagrange first articulated in his treatise on the three-body problem so many years ago. As you rest quietly now, perhaps you might picture these countless thousands of asteroids, drifting silently through the darkness of space at the same measured pace as Jupiter, neither gaining nor falling behind, their ancient surfaces unchanged since the earliest days of our solar system, patient witnesses to 4.5 billion years of cosmic history, waiting still to share their secrets with the distant spacecraft now making its unhurried way toward them across the vast and quiet distances between the worlds. On the second day of December, in the year 1995, an Atlas-sized rocket lifted away from Cape Canaveral in Florida, carrying within its payload ferrying a spacecraft that would come to redefine our relationship with the nearest star. The launch occurred in the early morning hours, when the Florida sky was still dark and the Atlantic Ocean stretched out invisible beneath the ascending vehicle, and aboard that rocket was the Solar and Heliospheric Observatory, known by the pleasingly simple acronym SOHO, a collaborative venture between the National Aeronautics and Space Administration and the European Space Agency that represented one of the most ambitious solar observation missions ever undertaken. The total cost of this endeavor approached $1 billion, a sum that reflected not merely the expense of building and launching a spacecraft, but the decades of scientific planning, international negotiation, instrument development, and careful engineering that had preceded that December morning. And as the rocket climbed through the atmosphere and eventually released SOHO to begin its journey toward the Sun-Earth Lagrange Point 1, the scientists and engineers who had devoted years of their professional lives to this mission watched with the quiet hope that their creation would function as intended, at least for the 2 years of its primary mission, which at the time seemed like a reasonable expectation for such a complex piece of space-based instrumentation. SOHO traveled for several months following its launch, making its way toward the first Lagrange point, that peculiar location in space where the gravitational influences of the Sun and Earth combine with orbital mechanics to create a region of relative stability, positioned approximately 1.5 million kilometers from our planet in the direction of the Sun. This distance, while enormous by any earthly standard, represents only about 1% of the total distance between Earth and the Sun, placing SOHO in a location from which it could observe our star without interruption, never passing behind Earth, never entering our planet's shadow, maintaining an unblinking watch on the solar surface and the space immediately surrounding it. The spacecraft does not, however, sit precisely at the mathematical point we call L1, for as we have discussed in our earlier considerations of these gravitational balance points, the collinear Lagrange points are not perfectly stable, and any object placed exactly at such a location would eventually drift away. Instead, SOHO follows what is known as a halo orbit, a gently curving path that carries it around the L1 point in a slow, looping trajectory, never straying too far from that special location but never quite settling there either, like a leaf caught in a very slow and very large eddy in an otherwise flowing stream. The spacecraft carries 12 scientific instruments, each designed to observe a different aspect of the sun or the solar wind that streams outward from it. And among these instruments is the Large Angle and Spectrometric Coronagraph, known by the abbreviation LASCO, which has become perhaps the most famous of SOHO's capabilities, largely because of the remarkable images it produces of the solar corona. A coronagraph is an instrument that creates an artificial eclipse within itself, using a small disk called an occulting disk to block out the brilliant light of the solar surface, allowing the much fainter light of the corona, that ethereal outer atmosphere of the sun, to become visible. The corona extends millions of kilometers into space, far beyond the visible edge of the sun, and it is through this region that the solar wind flows outward, carrying particles and magnetic fields toward Earth and the other planets. LASCO can observe material being ejected from the sun, watch it expand and propagate through the inner solar system, and provide crucial information about whether such material might be directed toward our planet, all from its vantage point at L1, where the spacecraft maintains its constant vigil. For the first several years following its arrival at L1, SOHO performed admirably, returning data that transformed our understanding of the sun in ways both expected and surprising. Scientists used the spacecraft's instruments to peer beneath the visible surface of the sun, employing techniques of aleoseismology that are somewhat analogous to the seismology used to study Earth's interior, observing the patterns of acoustic waves that propagate through the solar body and using those observations to deduce the structure and behavior of regions no instrument could directly see. These studies revealed unexpected complexities in the way the sun rotates, showing that different layers of the solar interior spin at different rates, with the outer convective zone exhibiting one pattern of rotation and the radiative zone beneath it another. And at the boundary between these regions, scientists discovered a layer of intense shearing motion where the different rotation rates meet, a region now understood to play a crucial role in generating the sun's magnetic field. Such discoveries came steadily in those early years, each one adding to the scientific harvest that justified the mission's considerable expense. And then, on the 25th of June in 1998, something went terribly wrong. A series of errors during a routine maintenance procedure led to a loss of attitude control, meaning the spacecraft could no longer point itself correctly, and without proper orientation, the solar panels could not face the sun, the antennas could not face Earth, and SOHO fell silent. The spacecraft tumbled slowly through space, its batteries draining, its instruments inactive, its future suddenly and unexpectedly uncertain. For weeks, mission controllers could not locate their spacecraft, could not communicate with it, could not determine whether it had sustained damage that would make recovery impossible. The situation seemed dire, and many within the scientific community began to accept that SOHO might be lost, that its mission might have ended prematurely in the cold darkness between Earth and Sun, with so much potential observation time never to be realized. What followed was an extraordinary demonstration of human ingenuity and the value of international cooperation in space exploration. The massive radio telescope at Arecibo in Puerto Rico, which at that time was the largest single-dish radio telescope in the world, was enlisted to help locate the missing spacecraft. by transmitting a powerful radar signal toward the region of space where SOHO was believed to be tumbling, and then listening for the faint echo of that signal bouncing off the spacecraft structure. Engineers were able to detect SOHO and determine its approximate location and motion. This radar detection, combined with subsequent efforts to re-establish communication and gradually restore the spacecraft's orientation, eventually succeeded in bringing SOHO back to operational status. The recovery took months of patient work, but by the end of 1998, SOHO was once again observing the Sun, its instruments functioning, its mission continuing. The spacecraft bore some damage from its ordeal, having been frozen through during the period when it could not maintain proper thermal control, but the fundamental capabilities remained intact, and the scientific observations resumed. The original mission plan called for SOHO to operate for 2 years, which at the time seemed sufficient to accomplish the primary scientific objectives. Yet as I speak these words to you now, SOHO is approaching 30 years of continuous operation, making it one of the most enduring and productive space missions in history. The spacecraft has outlived its original planned lifetime by more than a decade, continuing to return valuable data long after it might reasonably have been expected to fail. This longevity has allowed SOHO to observe multiple complete cycles of solar activity, watching as the Sun moved from periods of relative quiet to periods of maximum activity and back again, building a record of solar behavior that spans nearly 3 complete 11-year cycles. Such long-term observations are invaluable for understanding the patterns and variations in solar activity, for distinguishing between temporary fluctuations and longer-term trends, for building the kind of historical baseline against which future changes can be measured. Among the most unexpected contributions of SOHO has been its role as a comet discovery machine. The LASCO coronagraph, designed primarily to observe the solar corona and track material ejected from the Sun, also happens to be an excellent tool for spotting comets that pass close to the Sun, objects known as sun-grazing comets. These comets, many of which belong to families that share common orbital characteristics suggesting they originated from the breakup of larger parent bodies, pass so close to the Sun that they would be impossible to observe with ground-based telescopes, hidden as they are in the overwhelming glare of our star. But from LASCO's perspective, with the solar disk blocked by the occulting disk, these comets appear as small streaks of light moving against the background of stars, their tails streaming away from the Sun as solar radiation and solar wind strip material from their surfaces. What makes this aspect of SOHO's legacy particularly charming is that the majority of these comet discoveries have been made not by professional astronomers at major institutions, but by amateur observers around the world who examine LASCO images posted online, searching for the telltale signs of these solar visitors. More than 4,000 comets have been discovered using SOHO data, more than have been found by any other observatory in history, and a substantial portion of these discoveries carry the names of citizen scientists who spotted them first, ordinary people contributing to our understanding of the solar system from their homes. One of the enduring mysteries of solar physics concerns the temperature of the corona, which is, paradoxically, far hotter than the visible surface of the Sun beneath it. The solar surface, called the photosphere, has a temperature of approximately 5,500 degrees Celsius, which is certainly hot by any earthly standard but is much cooler than the corona, which reaches temperatures of 1 to 2 million degrees or even higher. This seems to violate our intuitive expectation that temperature should decrease as one moves away from a heat source, rather than increase, and explaining this apparent paradox has occupied solar physicists for decades. SOHO has contributed substantially to this ongoing investigation, providing observations that have helped constrain and refine the various theoretical mechanisms proposed to explain coronal heating, though a complete and universally accepted explanation remains elusive. The spacecraft's instruments have observed the magnetic structures that thread through the solar atmosphere, have watched the dynamic processes by which energy is transferred from the solar interior to the outer atmosphere, and have provided the kind of detailed, long-term observational record that is essential for testing theoretical predictions. From its position at L1, SOHO also serves a practical function of considerable importance for our technological civilization. Solar storms, events in which the sun releases large quantities of energetic particles and electromagnetic radiation, can have significant effects on Earth, disrupting radio communications, damaging satellites, threatening power grids, and posing radiation hazards to astronauts and even to passengers on high-altitude aircraft flying polar routes. By observing these events as they occur on the Sun and tracking the ejected material as it propagates outward through the inner solar system, SOHO provides advance warning of approaching solar storms, typically giving Earth between 15 and 45 minutes of notice before the arrival of the most energetic particles. This warning time, while short, can be sufficient to allow power grid operators to take protective measures, satellite controllers to safeguard sensitive electronics, and aircraft to alter their routes to reduce radiation exposure. SOHO thus serves not only as a scientific instrument but as a sentinel, watching over us from its distant post, alerting us to disturbances that might otherwise arrive without warning. And so SOHO continues its work, circling slowly around the L1 point in its halo orbit, its instruments pointed forever toward the Sun, gathering data that flows back across the 1.5 million kilometers to Earth, contributing to our understanding of the star upon which all terrestrial life depends. The spacecraft has survived its near-death experience in 1998, has outlived its original mission timeline by nearly 3 decades, has discovered more comets than any other observatory, has revealed secrets of the solar interior, and has provided countless warnings of approaching solar weather. It represents, in its quiet way, one of the great success stories of space exploration, a machine designed to observe the Sun for 2 years that has instead spent a generation doing so, returning value far beyond what its designers might reasonably have hoped. And as you listen to these words and feel yourself drifting towards sleep, you might imagine SOHO out there in the darkness between worlds, its instruments humming softly, its solar panels gathering the light of the Sun, continuing its patient work while we rest here on the planet it helps to protect. On the morning of December 25th, 2021, while much of the world was occupied with the quiet rituals of a holiday at home, a different kind of gathering was taking place along the northeastern coast of South America, in the tropical territory of French Guiana, where the European Space Agency maintains its primary launch facility near the small coastal town of Kourou. The air there is warm and heavy with humidity even in December, and the surrounding landscape is dense equatorial forest that stretches away in every direction, interrupted only by the cleared zones and towering infrastructure of the spaceport itself. It was from this place, at approximately 7:20 in the morning local time, that an Ariane 5 rocket lifted off from the launch pad carrying what many consider to be the most complex and ambitious scientific instrument ever constructed, the James Webb Space Telescope, folded carefully inside the rocket's protective fairing like an extraordinarily delicate piece of origami waiting to be unfurled in the darkness beyond our atmosphere. The choice of Kourou as the launch site was not arbitrary, for its location near the equator provides rockets with a beneficial boost from the Earth's rotation, reducing the amount of fuel required to reach the necessary velocity, and the Ariane 5 rocket had been selected years earlier as the launch vehicle precisely because its fairing was large enough to accommodate the telescope in its folded configuration, and because the rocket had established an excellent record of reliability over many years of service. The telescope itself had been transported across the Atlantic Ocean from California aboard a specially equipped cargo ship, a journey that took 16 days and covered roughly 5,600 nautical miles through the Panama Canal, because the folded observatory was simply too large and too fragile to be transported by aircraft. Every aspect of the mission had been planned with this same meticulous attention to logistics and risk, because there would be no opportunity to correct any mistakes once the telescope departed the Earth. The destination for this remarkable machine was not a low orbit around the Earth like that occupied by the Hubble Space Telescope, nor a distant orbit around the Sun or any other planetary body, but rather a very specific point in space known as the second Lagrange point of the Sun-Earth system, abbreviated simply as L2. This point lies approximately 1.5 million kilometers from Earth, which is roughly 4 times the distance from the Earth to the Moon, along the line extending from the Sun through the Earth and continuing outward into the outer regions of our solar system. At this particular distance, the combined gravitational influences of the Sun and the Earth create a region where a spacecraft can maintain a relatively stable position with respect to both bodies, orbiting the Sun at the same rate as the Earth while remaining perpetually positioned on the side of our planet that faces away from the Sun. The journey to this distant parking spot would take approximately 30 days, during which time the telescope would gradually coast outward from Earth while simultaneously undergoing a series of carefully choreographed deployment sequences that would transform it from a folded bundle of components into a fully operational scientific observatory. The complexity of these deployment sequences represented one of the most anxiety-inducing aspects of the entire mission for the engineers and scientists who had spent decades designing and building the telescope. Unlike the Hubble Space Telescope, which was launched fully assembled and could be serviced by astronauts aboard the space shuttle when problems arose, the James Webb Space Telescope was designed to operate far beyond the reach of any current crewed spacecraft, meaning that every component had to deploy correctly the first time without any possibility of hands-on repair. The mission planners had identified 344 individual mechanisms and events that could each, if they failed, potentially end the mission entirely, and these were soberly referred to as single-point failures because there was no backup, no redundancy, no second chance for any of them. The sun shield had to unfold correctly. The mirrors had to lock into their proper positions. The various booms and struts had to extend and latch precisely as designed. And all of this had to happen autonomously in the cold vacuum of space with only radio commands from Earth to guide the process. The primary mirror of the telescope, which is the large reflective surface that gathers light from distant celestial objects, measures approximately 6.5 meters in diameter, or roughly 21 feet, making it far too large to fit inside any existing rocket fairing in its deployed configuration. The solution to this problem was to construct the mirror from 18 separate hexagonal segments, each measuring about 1.3 meters across and weighing approximately 20 kilograms, which could be folded together like the petals of a flower for launch, and then carefully unfolded once the telescope reached space. These segments are made of beryllium, a lightweight metallite metal that maintains its shape extremely well across wide ranges of temperature, and each segment is coated with a microscopically thin layer of pure gold, approximately 100 nanometers thick, because gold is exceptionally good at reflecting infrared light, which is the portion of the electromagnetic spectrum that the telescope was primarily designed to observe. The golden color of these mirror segments has become one of the most recognizable visual features of the telescope, appearing in countless photographs and illustrations that have been published since the project began. Perhaps even more critical than the mirror, and certainly more complex to deploy, is the sun shield that protects the telescope's sensitive instruments from the heat and light of the sun, the Earth, and the Moon. This structure, when fully deployed, is approximately the size of a tennis court, measuring roughly 22 meters by 12 meters, and it consists of 5 separate layers of an extremely thin material called capton, which is a polyimide film that can withstand the harsh conditions of space while providing excellent thermal insulation. Each layer is coated with aluminum, and the 2 layers closest to the sun are also coated with a treated silicon compound that helps them withstand the intense solar radiation. The layers are separated from one another by small gaps, and this arrangement allows heat to radiate away between the layers rather than being conducted through them, creating a dramatic temperature difference between the side of the sun shield facing the sun and the side facing the telescope. On the sun-facing side, the temperature can reach approximately 85 degrees Celsius, while on the cold side, where the telescope's mirrors and instruments reside, the temperature drops to approximately negative 233 degrees Celsius, which is only about 40 degrees above absolute zero, the coldest possible temperature in the universe. This extreme cold is not merely a byproduct of the sun shield's design, but is in fact essential to the telescope's scientific mission, because the infrared light that the telescope was built to detect is essentially a form of heat radiation, and any warmth from the telescope itself would create a kind of thermal noise that would overwhelm the faint signals from distant stars and galaxies. By cooling the instruments to such extraordinarily low temperatures, the telescope can detect infrared light from objects that are incredibly faint and incredibly far away, including some of the earliest galaxies that formed in the universe more than 13 billion years ago. The second Lagrange point was chosen as the telescope's operational location precisely because it offers ideal conditions for maintaining these cold temperatures, as the spacecraft can position itself so that the Sun, the Earth, and the Moon are all on the same side, with the sun shield permanently blocking their light and heat from reaching the sensitive instruments on the other side. The development of the James Webb Space Telescope was an undertaking of almost unprecedented duration and cost in the history of space science. The project traces its origins back to discussions that began in 1989, just 3 years after the European Space Agency's Infrared Space Observatory had first demonstrated the scientific potential of space-based infrared astronomy, and the formal planning process began in the mid-1990s with a target launch date that was originally hoped to be around 2007. However, the extraordinary technical challenges involved in building such a sophisticated instrument, combined with various programmatic difficulties and funding constraints, caused the project to experience numerous delays and cost overruns over the following decades. The original cost estimate of approximately $1 billion grew steadily as the design was refined and the development work progressed, eventually reaching a final cost of approximately $10 billion by the time of launch, making it one of the most expensive scientific instruments ever constructed. The timeline stretched from the original target of 2007 to the actual launch date of 2021. Meaning that many of the scientists and engineers who began working on the project in its early years had retired or even passed away before the telescope finally reached space. The 30-day journey to L2 proceeded with remarkable smoothness, each deployment sequence executing successfully and each milestone being achieved on schedule or ahead of schedule. The sun shield unfolded over several days of careful operations, with each of the 5 layers being tensioned and separated from the others using a system of cables, pulleys, and motors that had been tested extensively on the ground but had never before been operated in the actual conditions of space. The primary mirror segments were unfolded and locked into position, And then over the following weeks, each segment was individually adjusted using tiny motors called actuators, which can move the segments by increments as small as 10 nanometers, or about 1/10,000th the width of a human hair, to bring the entire mirror into perfect optical alignment. By the end of January 2022, the telescope had arrived in its operational orbit around the L2 point, and the long process of commissioning and calibrating the instruments had begun. The first full-color scientific image from the James Webb Space Telescope was released to the public on July 12, 2022, during a special event at the White House in Washington, and it depicted a region of sky known as SMACS 0723, a galaxy cluster located approximately 4 billion light-years from Earth. The image revealed thousands of galaxies in extraordinary detail, including some that appeared stretched and distorted by the gravitational lensing effect of the foreground cluster, and among these were some of the most distant galaxies ever observed, their light having traveled for more than 13 billion years before reaching the telescope's golden mirrors. The scientific community received this image, and the many others that followed in the subsequent days and months, with a combination of profound satisfaction and eager anticipation, for the telescope was clearly performing even better than its designers had hoped, and the data it was collecting promised to revolutionize our understanding of the early universe, the formation of stars and planetary systems, and the atmospheres of planets orbiting other stars. The James Webb Space Telescope is not alone at the second Lagrange point, for this advantageous location has attracted several other spacecraft with similar requirements for thermal stability and unobstructed views of the cosmos. Among the most notable of these companions is the Gaia spacecraft, a mission of the European Space Agency that has been operating at L2 since 2014, with the goal of mapping the positions and motions of stars throughout our galaxy with unprecedented precision. Over the course of its mission, Gaia has measured the positions of approximately 1.8 billion stars, creating a three-dimensional map of the Milky Way that has transformed our understanding of the structure and history of our galactic home. The presence of multiple spacecraft at L2 does not create any risk of collision, because the region around the Lagrange point is vast and the spacecraft follow different orbital paths within that region, each tracing its own gentle curve around the mathematical point where the gravitational forces balance. The operational lifetime of the James Webb Space Telescope is ultimately limited by the amount of fuel it carries for station keeping, the small thruster firings that are periodically required to maintain its position in the unstable L2 region. The telescope was launched with enough fuel for a minimum of 10 years of operations, but the exceptional accuracy of the Ariane 5 launch, which placed the telescope on such a precise trajectory that very little fuel was needed for the initial course corrections, has extended the projected lifetime to approximately 20 years or perhaps even longer. When the fuel is eventually exhausted, the telescope will slowly drift away from its operational position and will no longer be able to maintain the precise orientation required for scientific observations. But until that distant day arrives, the golden eye of the James Webb Space Telescope will continue to gaze outward from its quiet parking spot 1.5 million kilometers from home, patiently collecting the ancient light of distant galaxies and revealing the universe to us in ways that were once beyond imagination. The story of why Lagrange points exist at all begins, perhaps surprisingly, with a confession of mathematical defeat, or at least the recognition of profound complexity that the human mind cannot easily untangle. When we place two bodies in space, say the Earth and the Moon, or the Sun and a single planet, we can calculate their motions with perfect precision using the equations that Newton gave us. The mathematics unfolds cleanly, predictably, and we can say with confidence where each body will be at any moment in the distant future. But when we introduce a third body, even one of negligible mass. The situation changes in ways that troubled mathematicians for centuries. And in 1890, the French mathematician Henri Poincaré proved something remarkable and somewhat unsettling about this arrangement. He demonstrated that the general three-body problem, the attempt to predict the motions of three gravitationally interacting objects, exhibits what we now call chaotic behavior, meaning that tiny differences in starting conditions lead to wildly different outcomes over time, and that no general closed-form solution exists for most configurations. This was not a failure of mathematics, but rather a discovery about the nature of certain physical systems, and it earned Poincaré a prize from the King of Sweden, though the path to that recognition involved the embarrassing correction of an error in his initial submission, which itself led to the deeper insights about chaos that made the work truly significant. And yet, despite this fundamental complexity, there exist special cases where stability and predictability emerge from the gravitational dance of three bodies, and these special cases are precisely what Joseph Louis Lagrange identified in 1772, more than a century before Poincaré's work on chaos. Lagrange was not attempting to solve the general problem, but rather examining a restricted version, one in which the third body has so little mass that it does not appreciably affect the motions of the other two. This is called the restricted three-body problem, and it describes situations like a spacecraft in the Sun-Earth system, or a small asteroid in the Sun-Jupiter system, where the tiny object responds to the gravitational fields of the two larger bodies but contributes essentially nothing to their behavior. Within this simplified framework, Lagrange discovered 5 points where a small object could, in principle, remain stationary relative to the two larger bodies, neither drifting toward one nor the other, but instead maintaining its position as if held there by invisible hands. To understand why these points exist, we must think about what it means for something to be stationary in a system where everything is moving. The Earth orbits the Sun, and the Moon orbits the Earth, and all of these motions continue ceaselessly. So when we speak of a Lagrange point being fixed, we mean fixed relative to the line connecting the two primary bodies. Imagine yourself sitting on the Earth, watching the Sun, and at a certain distance between you and the Sun, there exists a point that always maintains the same position relative to both, orbiting the Sun in exactly 1 year just as the Earth does, despite being at a different distance. For this to occur, the forces acting on any object placed there must combine in precisely the right way. And this is where the balance of gravitational pull and what we call centrifugal force in a rotating reference frame becomes essential to the explanation. When we analyze orbital mechanics, it is often convenient to adopt a rotating reference frame, one that spins along with the system so that the two primary bodies appear to stand still. In such a frame, an object experiences not only the gravitational attraction toward each of the two masses, but also an apparent outward force arising from the rotation itself, the centrifugal force that you feel when a car turns sharply and you seem to be pushed toward the outside of the curve. This is not a force in the traditional sense, but rather an artifact of the rotating coordinate system. Yet it is mathematically real and must be accounted for. At the Lagrange points, these three influences, the gravitational pull toward the larger body, the gravitational pull toward the smaller body, and the centrifugal tendency to fly outward, achieve a perfect balance, summing to zero so that an object placed there with the proper velocity will simply stay, rotating in lockstep with the system as if it were glued to an invisible scaffolding in space. The first three Lagrange points, designated L1, L2, and L3, all lie along the line connecting the two primary bodies, and their positions can be understood through relatively straightforward reasoning. L1 sits between the two bodies, at a location where the gravitational pull of the smaller body partially cancels the pull of the larger one, reducing the net sunward attraction to exactly what is needed for an orbit of the correct period. If we consider the Sun-Earth system, the L1 point lies roughly 1.5 million kilometers from Earth, toward the Sun, at a distance where the combined gravitational influences create the conditions for this delicate equilibrium. The calculation of this distance involves what is called the Hill sphere approximation, which estimates the region around a smaller body where its gravity dominates over the larger body's tidal forces. For L1, the distance from the smaller body can be approximated using the cube root of the ratio of the smaller mass to 3 times the larger mass, multiplied by the separation between the two bodies, though the actual calculation involves solving a quintic equation that has no simple algebraic solution and must typically be approached numerically or through successive approximation. L2 lies on the opposite side of the smaller body, in what might be called its gravitational shadow, though this term requires some clarification. At L2, both the Sun and the Earth pull in the same direction, toward the Sun, and one might wonder how balance could possibly be achieved there. The key is that L2 is farther from the Sun than the Earth is, and an object at that distance would normally require a longer orbital period, taking more than 1 year to complete a circuit. However, the Earth's gravity adds to the Sun's at this location, effectively increasing the central attraction and allowing an object there to orbit faster than it otherwise would, matching the Earth's yearly period despite being farther out. This is the shadow effect at work, where the combined gravity of both bodies equals precisely the amount needed for the required orbital velocity, and the result is another point of equilibrium, another cosmic parking spot roughly the same distance from Earth as L1 but in the opposite direction. L3 is perhaps the least intuitive, located on the far side of the larger body, opposite the smaller one. In the Sun-Earth system, L3 lies just beyond the Earth's orbit on the other side of the Sun, slightly farther out due to the subtle gravitational influence of the Earth pulling it outward. Science fiction has sometimes imagined a counter-Earth hiding at L3, permanently invisible behind the Sun, though the instability of this point and the many observations that would reveal such an object make this notion firmly fictional. And here we come to a crucial distinction between the Lagrange points. For L1, L2, and L3 are all unstable equilibria, while L4 and L5 possess a curious and conditional stability. The nature of this instability at the collinear points can be understood through the analogy of a marble balanced on a saddle, the kind of curved surface used for riding horses. If you place a marble at the very center of a saddle, it sits at a point where the surface curves upward in one direction and downward in the perpendicular direction, and while it is technically balanced, the slightest nudge will send it rolling off along the downward curving axis. There is no restoring force to push it back, no tendency to return to equilibrium, only the inevitable slide toward lower gravitational potential. Spacecraft stationed at L1 or L2 experience this same precariousness, drifting slowly away from the point unless they perform regular station-keeping maneuvers, small thruster firings that correct their positions and maintain the delicate balance. The James Webb Space Telescope at L2, for instance, requires periodic adjustments to remain near its designated location, gently nudging itself back toward equilibrium like a cyclist making constant tiny corrections to stay upright. L4 and L5, by contrast, are fundamentally different in their geometry, lying not along the line between the two bodies but at the vertices of equilateral triangles formed with those bodies. If you draw a line from the Sun to the Earth and then construct an equilateral triangle using that line as one side, The two remaining vertices mark the L4 and L5 points, one leading the Earth in its orbit by 60 degrees and one trailing by the same amount. The stability of these points is remarkable and counterintuitive, for they are not local gravitational valleys but rather gentle hilltops in the effective potential of the rotating system, and yet objects placed there tend to stay, wandering in slow loops around the point rather than escaping. The explanation for this apparent paradox lies in the Coriolis effect, another consequence of the rotating reference frame that we have not yet discussed. Just as the centrifugal force pushes outward in a rotating system, the Coriolis force acts perpendicular to the velocity of any moving object, deflecting it sideways in a manner that depends on the direction and speed of motion. When an object near L4 or L5 begins to drift away from equilibrium, the Coriolis force curves its path, bending it into a loop that brings it back toward the Lagrange point rather than allowing it to escape. The object traces out what are called tadpole orbits, small kidney bean-shaped paths that librate around the point like a gentle rocking motion, or sometimes larger horseshoe orbits that encompass both L4 and L5, slowly migrating from one to the other over many centuries. The restoring influence is not gravitational attraction toward the point itself, but rather this sideways deflection that converts outward motion into orbital motion around the equilibrium. However, this stability at L4 and L5 is not universal but depends on the mass ratio of the two primary bodies. Calculations show that stable libration is only possible when the mass of the larger body exceeds that of the smaller by a factor of approximately 24.96, a curiously specific number that emerges from the mathematical analysis of the Coriolis and centrifugal interactions. For the Sun-Jupiter system, this ratio is approximately 1047, comfortably exceeding the threshold, which explains why Jupiter's Trojan asteroids have accumulated in such impressive numbers over the age of the solar system, with thousands of rocky bodies trapped in stable tadpole orbits around Jupiter's L4 and L5 points. The Sun-Earth system also satisfies the criterion, though with a smaller ratio, and the Saturn-Tessis and Saturn-Dione systems harbor small moons at their Lagrange points. If the mass ratio falls below the critical value, the L4 and L5 points lose their stability, and objects placed there will eventually drift away. The practical application of these mathematical curiosities to space exploration came somewhat later than their theoretical discovery, and it is worth noting a 1961 paper by Robert Farquhar that first seriously proposed using Lagrange points for actual missions. Farquhar recognized that L1 and L2, despite their instability, offered remarkable vantage points for scientific observation, with L1 providing an unobstructed view of the Sun and L2 offering a location where a spacecraft could keep both the Sun and Earth behind it, shielding its instruments from their warmth and light. The station-keeping requirements, while not negligible, were modest enough that practical missions could be designed around them, and Farquhar's work laid the groundwork for the many L1 and L2 missions that have followed, from solar observatories to space telescopes to gravitational wave detectors. In thinking about the restricted three-body problem, it is worth remembering the assumptions that make it tractable. We assume that the third body has negligible mass, that the two primary bodies move in circular orbits around their common center of mass, and that all motion occurs in a single plane. Real systems deviate from these idealizations, with eccentric orbits, three-dimensional motion, and additional perturbing bodies complicating the picture. Yet the Lagrange points remain useful approximations, regions of relative calm in the gravitational landscape where spacecraft can loiter with minimal effort. The mathematics that Lagrange developed in the 18th century, building on Newton's foundations and anticipating Poincaré's insights into chaos, continues to guide mission planners today, a testament to the enduring power of careful analysis applied to the fundamental physics of gravitational attraction in a rotating universe. On the 12th of August in 1978, a spacecraft lifted off from Cape Canaveral in Florida, beginning a journey that would span decades and eventually capture the imagination of citizen scientists around the world. Though no one involved in that summer launch could have possibly imagined the winding path that lay ahead, the comet encounters, the long silence, and the remarkable attempt at resurrection that would come 36 years later. The spacecraft was called the International Sun-Earth Explorer 3, or ISA-3 for short, and it was the third in a series of satellites designed to study the complex relationship between our Sun and our planet, examining the streams of charged particles that flow outward from the solar surface and interact with Earth's magnetic field in ways both beautiful and consequential. The mission was a collaboration between NASA and the European Space Agency, reflecting the international cooperation that has so often characterized the peaceful exploration of space, and it carried a suite of instruments designed to measure magnetic fields, plasma waves, cosmic rays, and the various phenomena that occur in the regions of space influenced by solar activity. What made ISA-3 particularly special, and what earns it a place in the history of Lagrange point exploration, was its destination, for it was designed to become the first spacecraft ever to travel to the L1 point between Earth and the Sun, that gravitationally balanced location roughly 1.5 million kilometers sunward of our planet, where an object can maintain a relatively stable position with minimal fuel expenditure. Reaching this point required a trajectory quite different from those used for satellites in ordinary Earth orbit, and the person responsible for designing this pioneering path was a NASA engineer named Robert Farquhar, who had spent years studying the mathematics of Lagrange points and developing the techniques needed to place a spacecraft at one. Farquhar had written his doctoral thesis on the subject of station keeping near these gravitational balance points, and he understood better than almost anyone at the time how to thread a spacecraft through the complex gravitational influences of Earth and Sun to reach this cosmic parking spot and remain there in a controlled manner. The journey from Earth to L1 took approximately 3 months, a relatively leisurely transit that allowed mission controllers to check the spacecraft systems and ensure that everything was functioning properly before arrival at its operational location. In November of 1978, ISA-3 reached the vicinity of the L1 Lagrange point and began its primary mission of monitoring the solar wind, becoming the first human-made object to take up residence at one of these remarkable gravitational equilibrium locations. From this vantage point, the spacecraft could observe solar events before they reached Earth, providing an early warning of sorts for geomagnetic disturbances, and it could study the undisturbed solar wind in a region of space free from the complicating influence of Earth's magnetic field. The data it returned proved valuable for understanding the dynamic relationship between our planet and its parent star, and the mission was considered a success by any reasonable measure. But the story of ISA-3 was only beginning. For in 1982, with the spacecraft's primary mission completed and its instruments still functioning well, an audacious decision was made to repurpose it for an entirely different adventure. Robert Farquhar, the same engineer who had designed its original trajectory to L1, proposed something that had never been attempted before, a plan to send ISA-3 on a journey to intercept a comet, transforming a solar wind monitor into the first spacecraft ever to visit one of these ancient wanderers of the solar system. The comet chosen was Jacobina Zinner, a periodic comet that would pass through the inner solar system in September of 1985, and reaching it would require a trajectory of considerable complexity, involving not one but multiple flybys of the Moon to gradually reshape the spacecraft's orbit and fling it toward its new destination. The maneuvers required to accomplish this transformation were intricate in the extreme, involving 5 close passes of the Moon over a period of about 2.5 years, each flyby carefully calculated to bend the spacecraft's path in precisely the right way. On one memorable occasion, A3 passed just 120 kilometers above the lunar surface, threading through the gap between the Moon and its own orbital distance from Earth in a gravitational ballet of remarkable precision. These lunar flybys, occurring between late 1982 and late 1983, gradually built up the energy and changed the direction needed to send the spacecraft out of Earth's gravitational neighborhood entirely. And in December of 1983, ISA-3 left the Earth-Moon system behind, bound for its encounter with Jakobina nearly 2 years in the future. At this point, the spacecraft was rechristened with a new name befitting its new purpose, the International Cometary Explorer, or ICE, and it began the long coast toward its historic rendezvous. On the 11th of September in 1985, ICE became the first spacecraft ever to fly through the tail of a comet, passing approximately 7,800 kilometers from the nucleus of Jakobina and returning data about the plasma environment, magnetic fields, and energetic particles associated with this ancient body of ice and dust. The encounter lasted only a matter of hours, but it represented a genuine first in the history of space exploration, a milestone achieved not by a purpose-built comet mission but by a repurposed solar wind satellite guided by the creative trajectory design of Robert Farquhar and his colleagues. The spacecraft continued onward, eventually passing through the distant tail of Halley's Comet as well in March of 1986, adding another famous name to its list of encounters, though it remained much farther from Halley's nucleus than the dedicated spacecraft sent by other nations to study that famous visitor. After these cometary adventures, ICE continued to function, transmitting data about the interplanetary medium as it followed a long elliptical orbit around the Sun, an orbit that would eventually bring it back to the vicinity of Earth, though not for many decades. NASA maintained contact with the spacecraft through the early 1990s, gathering occasional measurements and tracking its position as it wandered through the inner solar system. But as budgets tightened and newer missions demanded attention, the resources needed to maintain the aging Explorer became harder to justify. In 1997, with the spacecraft still technically functional but no longer a scientific priority, NASA terminated regular contact with ISE-3/ICA, leaving it to continue its lonely orbit in silence, a small cylinder of metal and electronics circling the Sun with no one listening to its faint radio transmissions. For 17 years, the spacecraft drifted in quiet solitude, its signal going unheard, its instruments perhaps still gathering data that no one would ever receive, its trajectory slowly carrying it back toward the planet from which it had launched so long ago. The story might have ended there, a successful mission gradually forgotten as newer and more capable spacecraft captured the public imagination and the scientific community moved on to other questions. But in 2014, a group of citizen scientists decided to attempt something remarkable, an effort to reawaken this sleeping wanderer and restore communication with a spacecraft that had been silent for nearly 2 decades. The ISE-3 reboot project was led by Dennis Wengo and Keith Cowan, 2 individuals with backgrounds in space technology and science journalism who had followed the story of the aging spacecraft and recognized that its return to Earth's vicinity presented a unique opportunity. The spacecraft was approaching a point in its orbit where it would pass close enough to Earth that communication might be possible with sufficient effort and the right equipment, and if contact could be re-established, there was a chance that the spacecraft could be commanded to fire its thrusters and enter a new orbit, perhaps even returning to the L1 Lagrange point where it had begun its operational life 36 years earlier. The project was ambitious, requiring not only the technical expertise to communicate with decades-old hardware, but also the funding to pay for time on the large radio telescopes needed to receive the spacecraft's weak signals and transmit commands powerful enough to reach it across the vastness of space. Turning to the emerging model of crowdfunding, the Reboot project launched a campaign that captured the imagination of space enthusiasts around the world, raising approximately $160,000 from thousands of individual donors who wanted to be part of this quixotic attempt at resurrection. The money was used to secure time on the Great Arecibo radio telescope in Puerto Rico, a 1,000-foot dish nestled in a natural limestone sinkhole that was among the most sensitive radio receivers on Earth, and to develop the software and hardware needed to generate the specific signal formats that ICE-3 had been designed to receive so many years ago. The original communication protocols had been lost or archived in formats that were difficult to access, and the team had to piece together the technical details from old documentation and the memories of engineers who had worked on the mission in its early days. On the 29th of May in 2014, the team succeeded in re-establishing contact with ICE-3, detecting its carrier signal and confirming that the spacecraft was still alive after all those years of wandering in silence. It was a moment of genuine triumph for the citizen scientists involved, a demonstration that dedicated amateurs working with recovered technology and crowd-funded resources could accomplish what might have seemed impossible, reaching across 36 years and millions of kilometers to touch a piece of human engineering that had been given up for lost. The spacecraft responded to commands, its systems still functioning to a surprising degree given the decades of radiation exposure and thermal cycling it had endured, and the team began preparing to attempt the thruster firings that would be needed to adjust its trajectory. But the moment of heartbreak came when the thrusters were tested and failed to produce the expected result, and subsequent analysis revealed that the nitrogen gas used to pressurize the spacecraft's fuel system had been depleted over the long years of its journey, leaving the hydrazine propellant unable to flow to the engines in the way required for controlled burns. Without functioning thrusters, there was no way to alter ICE-3's trajectory, no way to capture it into a new orbit around Earth or return it to the L1 point where it had made history so long ago. And the team was forced to accept that while they had successfully awakened the sleeping spacecraft, they could not redirect its wandering path. They continued to communicate with it for as long as possible, gathering what data they could from its still functioning instruments, until the increasing distance eventually made further contact impractical. Today, ICE-3 continues its endless orbit around the Sun, a small artifact of human ambition and engineering following a path that occasionally brings it back near the planet of its origin. It is expected to return to the vicinity of Earth around 2031, passing by once again before swinging back out into the solar system. And perhaps by then new technologies or new efforts will allow another attempt at communication, another chance to reach out across the decades to this persistent traveler. The spacecraft represents something poignant about our relationship with the machines we send into space, the way they outlive our attention and continue their journeys long after we have stopped listening, the way they can sometimes be found again and brought back into the fold of human awareness through dedication and ingenuity. The story of ICE-3 is one of firsts and lasts, of pioneering achievements and quiet endings, of a spacecraft that demonstrated the utility of Lagrange points, visited a comet, fell silent for years, and was briefly resurrected by citizens who cared enough to try. It is a story that might help ease you towards sleep now. This tale of patient wandering and unexpected reunion, of nitrogen that slowly leaked away over decades and thrusters that finally refused their commands, of a small machine still circling the sun in the darkness, carrying its instruments through space whether anyone is listening or not, enduring in its orbit as you rest and dream. And now we turn our attention to a rather remarkable gathering of spacecraft, a small collection of machines that drift together in the darkness, approximately 1.5 million kilometers from Earth, positioned at that first Lagrange point we discussed earlier, the one that sits between our planet and the Sun. This cluster of satellites, assembled gradually over the course of nearly 3 decades, forms what we might call humanity's early warning system for the weather that travels through space, the invisible storms that flow outward from our star and occasionally wash over our world with consequences that can be quite significant, though we shall speak of those consequences in due time, and in the gentle manner appropriate to this hour. The spacecraft stationed at the Sun-Earth L1 point have a rather important job, you see, because they occupy a position that allows them to observe the Sun and measure what flows from it before that material reaches our planet. The solar wind, that continuous stream of charged particles emanating from the Sun's outer atmosphere, passes by these Sentinel spacecraft first, giving them the opportunity to sample its composition and measure its speed and density, and then to send word back to Earth that something is approaching. It is rather like having a weather station positioned upstream on a river, where it can observe the water and report what is coming long before that water reaches the towns and fields further downstream. The distance between L1 and Earth provides a buffer of time, typically between 15 and 45 minutes depending on the speed of the solar material, and this advance notice, brief though it may seem, can be quite valuable indeed. Among the earliest of these sentinels, and still faithfully operating after more than a quarter century, is a spacecraft called the Advanced Composition Explorer, though it is known more commonly by its abbreviated name, AC. This spacecraft was launched in August of 1997, lifted into the sky aboard a Delta II rocket, and it made its way to the L1 point where it has remained ever since, slowly orbiting the gravitationally balanced region while keeping its instruments pointed toward the Sun. The primary purpose of ACE is to measure the composition of the solar wind, to determine precisely which elements and isotopes are carried in that stream of particles, and to study the energetic particles that are accelerated by solar flares and coronal mass ejections. The spacecraft carries 9 scientific instruments, and together they provide detailed information about the material that flows past, sampling the solar wind much as one might sample water from a stream to learn what minerals and sediments it contains. After more than 27 years of continuous operation, AC continues to transmit data back to Earth, a testament to careful engineering and perhaps a bit of good fortune as well, and it remains a valuable member of the L1 fleet despite being one of the older spacecraft still active in that region. A newer addition to this collection of solar observers is a spacecraft with the rather lengthy name of the Deep Space Climate Observatory, which is abbreviated to DSCOVR and pronounced, rather pleasantly, as Discover. This spacecraft was launched in February of 2015 and arrived at L1 later that same year, where it took up the important duty of providing operational space weather warnings for the United States National Oceanic and Atmospheric Administration. The primary instruments aboard DSCOVR measure the solar wind speed and density, as well as the strength and orientation of the interplanetary magnetic field, and this information is transmitted to Earth with as little delay as possible so that forecasters can assess the potential impacts of incoming solar storms. The warnings that DSCOVR provides typically give between 15 and 45 minutes of advance notice before disturbed solar wind conditions reach Earth, and while this may not sound like a great deal of time, it can be sufficient for power grid operators to take protective measures, for satellite operators to place their spacecraft in safe modes, and for various other preparations to be made. But DSCOVR is perhaps equally well known for something rather different, a camera called EPIC, which stands for Earth Polychromatic Imaging Camera. This instrument faces not toward the Sun but back toward Earth, and from its vantage point 1.5 million kilometers away, it captures images of the entire sunlit face of our planet. Because DSCOVR is positioned between Earth and the Sun, the Earth it sees is always fully illuminated, always showing its daylit hemisphere, and the EPIC camera takes images throughout the day as different parts of the planet rotate into view. These images are made available to the public, and they show our world as a complete sphere, blue and white and green and brown, hanging in the darkness of space, a perspective that is both scientifically useful and, many would say, rather beautiful in its own quiet way. The camera captures images in 10 different wavelengths of light, allowing scientists to study atmospheric ozone, vegetation, cloud height, and various other phenomena, so it serves a genuine scientific purpose beyond the simple wonder of seeing our planet whole. The history of DSCOVR is itself rather interesting, and involves a period of some controversy followed by a long hibernation before the spacecraft finally reached its intended destination. The original concept for the mission was developed in the late 1990s, and it was championed quite publicly by the then Vice President of the United States, Al Gore, who envisioned a spacecraft that would provide a continuous view of the sunlit Earth, streaming images back to our planet that could be made freely available to anyone who wished to see them. The idea was that this perspective, showing Earth as a small and fragile world, might inspire a greater sense of environmental awareness. Because of this association with the Vice President, the mission acquired the informal name GORSAT, a designation that was sometimes used with affection and sometimes with derision depending on the political inclinations of the speaker. The spacecraft was built and its instruments were completed, but following the change in administration after the 2000 election, the mission was cancelled before launch and the fully assembled spacecraft was placed into storage. For 14 years, DSCOVR sat in a clean room at the Goddard Space Flight Center, waiting for a purpose that might never come. It was a rather expensive piece of equipment to simply set aside, but such things do happen in the world of government-funded space programs, where priorities shift and budgets are allocated according to decisions that are not always purely scientific. Eventually, however, the need for a replacement for the aging ACE spacecraft became pressing, and DSCOVR was retrieved from storage, refurbished, and given a new primary mission focused on space weather monitoring rather than Earth observation, though the EPIC camera was retained and continues to provide those lovely images of our planet. The spacecraft that spent 14 years waiting in a clean room now serves as one of the primary sentinels watching over our technological civilization, warning of the solar storms that can disrupt our power grids and satellites, a second life that its original designers might not have anticipated but would likely appreciate nonetheless. Another veteran of the L1 region is the WIND spacecraft, which has been operating even longer than ACE. WIND was launched in November of 1994, making it now 30 years old, and it was designed to study the solar wind and the interaction between the solar wind and Earth's magnetosphere. Over its long operational life, WIND has made detailed measurements of the plasma, energetic particles, and magnetic fields in the solar wind, contributing enormously to our understanding of how material from the Sun flows through the inner solar system. The spacecraft has completed a complex series of orbital maneuvers over the years, including periods spent at the L1 point, excursions through the deep magnetotail of Earth, and various other trajectories designed to sample different regions of near-Earth space. Like AC, WIND continues to operate and return useful data, a remarkable achievement for a spacecraft that has been exposed to the harsh radiation environment of space for 3 decades. Not all missions to the L1 point are concerned with solar monitoring. Between 2015 and 2017, a spacecraft called LISA Pathfinder occupied a halo orbit around L1, conducting an entirely different sort of experiment. LISA Pathfinder was a technology demonstration mission operated by the European Space Agency, and its purpose was to test the techniques and technologies that would be needed for a future space-based gravitational wave observatory. The detection of gravitational waves, those ripples in the fabric of spacetime predicted by Einstein and first directly observed in 2015 by ground-based detectors, requires extraordinarily precise measurements of distance, and a space-based detector would need to track the positions of test masses with accuracy measured in picometers. LISA Pathfinder carried 2 small gold-platinum cubes and demonstrated that these test masses could be kept in nearly perfect free fall, isolated from all external forces to an unprecedented degree. The mission was a complete success, and it paved the way for the future LISA mission, a full-scale gravitational wave observatory that will use 3 spacecraft separated by millions of kilometers. Though LISA Pathfinder was not monitoring the Sun or providing space weather warnings, its presence at L1 demonstrated the versatility of this orbital location and the variety of scientific purposes it can serve. The newest member of the L1 fleet is Aditya L1, India's first space-based solar observatory, which was launched in September of 2023 and arrived at its destination at the beginning of January 2024. The spacecraft is named for the Sanskrit word for the sun, and it carries 7 scientific instruments designed to study the solar corona, solar emissions, and the particle environment in space. The mission represents a significant achievement for the Indian Space Research Organization, adding India to the small group of nations that have successfully placed spacecraft at the Lagrange points. Aditya L1 will study the mechanisms of coronal heating, the triggers for solar flares and coronal mass ejections, and various other aspects of solar physics, contributing to the growing body of knowledge that helps us understand and predict the behavior of our parent star. The practical importance of all this solar monitoring becomes clear when we consider what can happen when the Sun sends a particularly energetic burst of material toward Earth without adequate warning. In March of 1989, a severe geomagnetic storm caused by a coronal mass ejection struck our planet and induced powerful electric currents in the ground across a wide area. In the Canadian province of Quebec, these ground-induced currents overwhelmed the protective systems of the Hydro-Quebec power grid, causing a cascade of failures that left 6 million people without electricity for 9 hours. Transformers were damaged, and the economic cost of the blackout was substantial. The storm came with relatively little warning, because the monitoring systems of that era were far less capable than what we have today, and the rapid onset of the most severe conditions caught grid operators off guard. Again in October and November of 2003, a series of powerful solar storms known collectively as the Halloween storms caused widespread disruptions to satellites and communication systems. Several satellites experienced anomalies and some suffered permanent damage. High-frequency radio communications were disrupted, and airlines were forced to reroute flights away from polar regions where the radiation environment had become hazardous. These events served as a reminder that our increasingly technological society has become increasingly vulnerable to the storms that rage unseen in the space between the Sun and Earth, and they reinforce the importance of maintaining a robust system for monitoring solar activity and providing advance warning of dangerous conditions. The fleet of spacecraft at L1 provides this monitoring with a degree of redundancy that is quite important, because individual spacecraft can and do experience failures, and the continuous coverage that is needed for reliable space where the forecasting cannot depend on any single machine. When multiple spacecraft are watching the Sun together, the loss of one does not leave us blind, and the data from different instruments can be compared and combined to give a more complete picture of conditions in space. The spacecraft do not simply sit motionless at the L1 point, of course, but rather follow halo orbits around it, tracing looping paths that keep them in the general vicinity while avoiding the zone directly along the Sun-Earth line where solar radio emissions would interfere with their communications with Earth. These halo orbits are carefully designed to maintain the spacecraft in useful positions while avoiding the communications difficulties that would arise from having the Sun directly behind them as seen from Earth. Looking toward the future, the European Space Agency is planning a mission called Vigil that will be positioned not at L1 but at the L5 point, 60 degrees behind Earth in its orbit around the Sun. From this location, Vigil will be able to observe the side of the Sun that is about to rotate into view from Earth, providing advance notice of active regions and potential sources of solar storms several days before they would be visible from L1 or from our planet. This side view will also allow better tracking of coronal mass ejections as they travel outward from the Sun, giving more accurate predictions of their speed and direction. The combination of monitors at L1 watching what is directly approaching and observers at L5 watching what is coming around the Sun's limb will provide a more complete picture of space than either vantage point could offer alone. And so the L1 point continues to serve as a gathering place for these patient machines, each one keeping watch in its own way, measuring particles and fields and light, sending their data home across 1.5 million kilometers of empty space. They orbit slowly around that invisible point of gravitational balance, neither falling toward the Sun nor drifting back toward Earth, maintaining their positions year after year with occasional small adjustments from their thrusters. The warnings they provide, measured in minutes, can make the difference between a power grid that weathers a storm safely and one that collapses into darkness, between a satellite that enters safe mode in time and one that suffers permanent damage. It is a quiet vigil that they keep, unnoticed by most of us, but important nonetheless, and they will continue keeping it for as long as their fuel holds out and their instruments keep functioning, measuring the wind that blows from the Sun. The second Lagrange point, which astronomers and mission planners refer to simply as L2, sits approximately 1.5 million kilometers from Earth, positioned on the side of our planet that faces away from the Sun, and it has become, over the past 2 decades, what one might reasonably describe as the most valuable piece of empty space in our entire solar system. This particular location, where the gravitational influences of the Sun and Earth combine with the orbital motion of any object placed there to create a region of relative stability, offers something that no other accessible point in space can provide with such elegant simplicity, which is an unobstructed view of the deep universe combined with a thermal environment so consistently cold and dark that the most sensitive instruments ever constructed by human hands can operate there without interference from the warmth and light that would otherwise overwhelm their delicate detectors. To understand why L2 became the premier location for space telescopes, particularly those designed to observe in infrared wavelengths, or to detect the faintest signals from the most distant reaches of the cosmos, one must first appreciate the fundamental challenge that faces any observatory attempting to peer into the cold depths of space. Everything that possesses warmth emits infrared radiation, including the telescope itself. And if you are trying to detect the extraordinarily faint infrared glow from a galaxy billions of light-years away, or the subtle temperature variations in the cosmic microwave background radiation that has been traveling through the universe for nearly 14 billion years, then any stray heat or light from nearby sources becomes an insurmountable problem, drowning out the very signals you are attempting to measure, like the sound of a whisper lost beneath the noise of a crowded room. At the second Lagrange point, a telescope can position itself so that the Sun, Earth, and Moon all remain on roughly the same side of the spacecraft at all times, and this arrangement means that a single sunshield, a carefully engineered barrier of reflective and insulating materials, can block the heat and light from all three of these bright objects simultaneously. The telescope itself, and particularly its mirrors and detectors, can then cool to temperatures approaching the absolute cold of deep space, sometimes reaching conditions colder than 200 degrees below zero on the Celsius scale. And at such temperatures, the observatory's own infrared emissions become negligible, allowing it to detect the whisper-faint signals from objects so distant that their light has been traveling since the universe was young. The thermal stability at L2 is remarkable precisely because nothing changes very much from the perspective of the spacecraft, at least not in ways that matter for the instruments on board. Unlike a telescope in low Earth orbit, which passes in and out of Earth's shadow every 90 minutes or so, experiencing dramatic swings in temperature as it moves from blazing sunlight into complete darkness and back again, a telescope at L2 maintains a constant orientation with respect to the Sun, Earth, and the deep sky it observes. This steadiness, this lack of thermal cycling and the mechanical stresses it produces, allows the telescope structure to remain dimensionally stable, which is essential when you are trying to focus light with mirrors that must maintain their precise shapes to within a fraction of a human hair. The continuous deep space viewing available at L2 means that telescopes stationed there can observe their targets for extended periods without interruption, building up the long exposure times necessary to collect enough photons from faint and distant objects to create meaningful images or spectra. There is no Earth looming into the field of view every 45 minutes, no bright limb of our planet reflecting sunlight into the telescope optics, no atmosphere absorbing and distorting the incoming radiation. The sky, as seen from L2, is as dark and clear as it can possibly be while remaining within practical reach of missions launched from Earth, and this makes it the ideal location for the most ambitious astronomical observatories humanity has ever constructed. The scientific legacy of L2 began in earnest with the Wilkinson Microwave Anisotropy Probe, known by its abbreviation WMAP, which was launched in June of 2001 and operated until it was decommissioned in late 2010. This spacecraft was designed to measure the cosmic microwave background radiation, which is the faint afterglow of the Big Bang itself, the oldest light in the universe, released approximately 380,000 years after the moment of creation, when the cosmos had cooled sufficiently for atoms to form and for light to travel freely through space without being scattered by the hot plasma that had previously filled all of existence. By mapping the tiny temperature variations in this ancient radiation with unprecedented precision, variations that amounted to only a few hundred millionths of a degree across different regions of the sky, WMAP provided data that allowed cosmologists to determine the age of the universe with remarkable accuracy. The figure they arrived at, through careful analysis of the patterns in the cosmic microwave background, was approximately 13.77 billion years, give or take about 40 million years either way, and this measurement represented a triumph of observational cosmology, transforming what had once been philosophical speculation about the age of existence into a scientific determination supported by rigorous evidence. Following in the footsteps of WMAP came the Planck Observatory, a mission of the European Space Agency that launched in May of 2009 and operated until October of 2013. Planck was designed to map the cosmic microwave background with even finer resolution and greater sensitivity than its predecessor, and it succeeded magnificently in this aim. producing detailed images of the temperature fluctuations in the ancient light that revealed subtle features invisible to previous instruments. The Planck data refined our understanding of cosmological parameters, including the age of the universe, the proportions of ordinary matter, dark matter, and dark energy that compose it, and the rate at which the cosmos is expanding. And these results continue to inform theoretical models of how the universe began, evolved, and will continue to develop in the eons to come. Arriving at L2 alongside Planck in 2009 was the Herschel Space Observatory, which carried the largest mirror ever launched into space at that time, a primary mirror measuring 3.5 meters in diameter, designed to collect far-infrared and submillimeter radiation from the cold and dusty regions of the universe where stars and planetary systems are born. Herschel operated until April of 2013, when its supply of liquid helium coolant, necessary to keep its detectors at temperatures close to absolute zero, was finally exhausted, and during its operational lifetime it observed the formation of stars in distant galaxies, studied the composition of comets and asteroids in our own solar system, and provided insights into the complex chemistry of interstellar space that continues to inform our understanding of how the raw materials of planets and life are distributed throughout the cosmos. The Gaia mission, launched by the European Space Agency in December of 2013, represents a somewhat different application of L2's advantages, though one no less remarkable in its scope and ambition. Rather than studying the distant universe or the cosmic microwave background, Gaia was designed to create the most detailed three-dimensional map ever made of our own Milky Way galaxy, measuring the positions, distances, and motions of stars with a precision that had never before been achieved. Operating from L2, where the stable thermal environment allows its optical systems to maintain the extraordinary precision required for such measurements, Gaia has catalogued approximately 1.8 billion stars, determining their distances through the method of parallax, measuring how their apparent positions shift slightly as Gaia orbits the Sun over the course of a year. The data from Gaia has transformed our understanding of the structure and history of our galaxy, revealing streams of stars that were stripped from smaller galaxies consumed by the Milky Way billions of years ago, mapping the warped and twisted shape of the galactic disk with unprecedented detail, and providing fundamental calibrations that allow astronomers to measure distances throughout the universe with greater accuracy than ever before. Gaia continues to operate at L2, slowly building an ever more complete census of the stellar neighborhood we call home. In July of 2019, the SPECTRA-G telescope was launched to L2 through a collaboration between Russia and Germany, carrying instruments designed to survey the sky in X-ray wavelengths. X-ray astronomy reveals the most violent and energetic phenomena in the universe, including the superheated gas surrounding black holes, the remnants of exploded stars, and the vast reservoirs of hot plasma that fill the spaces between galaxies in massive clusters. From its position at L2, SPECTRA-G has been conducting an all-sky survey, mapping the distribution of X-ray sources across the entire celestial sphere and providing data that will inform our understanding of high-energy astrophysics for decades to come. The most recent major addition to the observatory community at L2 is the Euclid telescope, launched by the European Space Agency in July of 2023 with a mission to study the nature of dark energy and dark matter, two of the most profound mysteries in modern physics. Dark energy, the unknown force that appears to be causing the expansion of the universe to accelerate, and dark matter, the invisible mass that holds galaxies together but does not interact with light, together make up roughly 95% of the total energy content of the cosmos, yet their fundamental nature remains unknown. Euclid will observe billions of galaxies across a significant fraction of the sky, using their shapes and distributions to map the large-scale structure of the universe and trace how that structure has evolved over cosmic time, providing clues that may help physicists understand what these mysterious components actually are. The logistics of operating spacecraft at L2 present challenges quite different from those faced by missions in low Earth orbit. At a distance of approximately 1.5 million kilometers, radio signals traveling at the speed of light take about 5 seconds to make the round trip between Earth and a spacecraft at L2, introducing a delay that, while manageable, requires careful planning for any operations that must respond to changing conditions. The data rates that can be achieved across such distances are limited by the power available to the spacecraft transmitters and the size of the antennas on both ends of the communication link. And so missions to L2 must be designed with careful attention to how quickly they can transmit their observations back to Earth. Perhaps most significantly, the distance to L2 means that servicing missions of the kind that famously repaired and upgraded the Hubble Space Telescope are simply not practical with current technology. Hubble orbits only a few hundred kilometers above Earth's surface, close enough that space shuttle crews could visit it repeatedly, replacing instruments and correcting problems that would otherwise have ended the mission. No such rescue is possible for telescopes at L2, and so these spacecraft must be designed with extraordinary reliability and must carry all the resources they will need for their entire operational lifetimes, including, in many cases, the finite supplies of coolant that allow their infrared detectors to function. When missions at L2 reach the end of their operational lives, they cannot simply be left in place, as their presence in this valuable region of space could eventually interfere with future observatories. Instead, decommissioned spacecraft are typically given a final set of commands that push them out of the L2 region and into what is called a graveyard orbit, a heliocentric path that takes them safely away from L2 and ensures they will not pose a hazard to successor missions. This gentle departure, using the last of the spacecraft's fuel reserves, represents a considered act of cosmic housekeeping, preserving the cleanliness of this remarkable observation point for generations of telescopes yet to come. Looking to the future, the next major observatory planned for L2 is the Nancy Grace Roman Space Telescope, a NASA mission expected to launch in the mid-2020s. Carrying a primary mirror the same size as Hubble's, but with instruments designed to survey much larger areas of sky in each observation, the Roman telescope will study dark energy, search for planets around other stars, and conduct surveys of the cosmos that will complement and extend the work of other great observatories. Its arrival at L2 will add another member to the community of spacecraft that have made this distant gravitational balance point into humanity's premier window on the universe, a vantage point from which we can study the cosmos with clarity and precision that would be impossible from any other location within our practical reach. The story of L2 is one of quiet triumph, of careful engineering and patient observation, of telescopes that have reshaped our understanding of the cosmos while hovering in the cold darkness beyond the moon, protected from the warmth of the sun by cleverly designed shields and sustained by radio links stretching across 1.5 million kilometers of empty space. These spacecraft have measured the age of the universe, mapped the structure of our galaxy, studied the births and deaths of stars, and begun the long work of understanding the mysterious forces that govern the fate of all that exists. And they have done so from a location that, until recent decades, existed only as a mathematical curiosity in the equations of celestial mechanics. In the early 1970s, a Princeton physics professor named Gerard Kitchener-Neal began to ask his students a question that would eventually reshape how many people imagine the human future in space. And this question, posed quietly in seminar rooms and lecture halls, was deceptively simple in its framing. For O'Neill wanted to know whether the surface of a planet was truly the best place for an expanding technological civilization to make its home among the stars, or whether there might be other possibilities, other arrangements, that could prove more practical and more abundant in the long centuries ahead. O'Neill had been working primarily on particle physics, designing accelerators, and studying the fundamental forces of nature. But he found himself drawn toward this different sort of problem, one that combined engineering and imagination in equal measure, and he encouraged his students to think carefully about the constraints and opportunities that space itself presented, not as a hostile void to be crossed as quickly as possible, but as an environment with its own particular advantages, its own resources waiting to be used, its own strange and quiet freedoms that a planetary surface could never quite provide. The results of this thinking appeared in 1974, when O'Neill published a paper in the journal Physics Today, a well-respected publication that reached physicists across many disciplines. And in this paper, he outlined his proposal for large rotating space habitats that could house permanent human populations far from Earth, structures that would generate their own gravity through the gentle physics of rotation, that would grow food under artificial sunlight, and that would provide, in O'Neill's careful calculations, a quality of life that might eventually exceed what any terrestrial nation could offer its citizens, all while leaving Earth's surface to recover from the strains of industrialization and population growth. The Physics Today paper was technical but accessible, filled with equations and engineering estimates, and it sparked considerable interest among readers who had perhaps grown accustomed to thinking of space colonization only in terms of planetary surfaces, of domed cities on Mars or pressurized bases on the Moon, whereas O'Neill was suggesting something rather different, something that treated empty space itself as real estate, as territory that could be shaped and filled and made comfortable through human effort and ingenuity, with the Lagrange points serving as natural harbors where these great structures might safely rest. 2 years later, in 1976, O'Neill expanded his ideas into a book called The High Frontier, which brought his concepts to a much wider audience and presented them in language that general readers could follow without advanced physics training. And this book became something of a sensation among certain enthusiasts, inspiring a generation of space advocates who found in O'Neill's pages a vision of the future that seemed both technically grounded and genuinely hopeful. A future where humanity might spread throughout the solar system not as struggling colonists on hostile worlds, but as prosperous citizens of self-sufficient habitats drifting peacefully through the cosmic dark. The design that O'Neill became most closely associated with was an enormous cylindrical structure, sometimes called an O'Neill cylinder in his honor, consisting of 2 counter-rotating cylinders arranged in parallel, each one measuring approximately 5 miles in length and 1 mile in diameter, rotating slowly to produce artificial gravity along their inner surfaces through the outward push of centripetal acceleration. And these paired cylinders would spin in opposite directions so that their angular momenta would cancel out, making the overall structure easier to orient and control. A clever bit of engineering that emerged from careful thought about the practical challenges of maintaining such enormous objects in stable positions over decades and centuries. Inside these cylinders, O'Neill envisioned landscapes that would feel surprisingly familiar to Earth-born residents, with soil and water and atmosphere and vegetation arranged along the curving interior surface, with rivers and lakes reflecting sunlight admitted through vast windows, with weather patterns that could be engineered for pleasant consistency, and with room enough for towns and farms and forests, for parks and recreation areas and all the spaces that human beings seem to need for their psychological well-being, so that life aboard an O'Neill cylinder might feel less like existence in a spacecraft and more like residence in a particularly well-designed valley, curved overhead in ways that would eventually seem natural to those who grew up knowing nothing else. The cylinders would house millions of people at full capacity, representing populations comparable to small nations, and they would be largely self-sufficient in terms of food and basic manufactured goods, with economies that might specialize in particular industries, perhaps zero-gravity manufacturing or solar energy collection or the processing of asteroidal materials, trading with other habitats and with Earth through networks of transportation that O'Neill believed would eventually become as routine and unremarkable as shipping lanes on terrestrial oceans, connecting the scattered communities of human space into a civilization that spanned the inner solar system. Around the same time that O'Neill was developing his cylinder concept, NASA sponsored a summer study at Stanford University in 1975, bringing together engineers and scientists to examine the possibility of space colonization with more institutional rigor. And this study produced an alternative design called the Stanford Torus, which was a wheel-shaped habitat roughly 1 mile in diameter, rotating to produce gravity along its outer rim, capable of housing perhaps 10,000 people in a more modest arrangement that might serve as a stepping stone toward the larger cylinders O'Neill envisioned, a proof of concept that could be built with nearer-term technologies and budgets. The Stanford Torus appeared in numerous illustrations during this period, often depicted with a large central hub for docking spacecraft, with spokes connecting this hub to the rotating wheel, and with enormous mirrors directing sunlight into the habitat's interior. And these images became iconic representations of a certain kind of space future, appearing in textbooks and magazines and presentations, helping to establish a visual language for off-world settlement that differed markedly from the cramped modules and sterile corridors that characterized actual spaceflight hardware of the era. The Princeton Space Studies Conferences, held between 1974 and 1977, brought together academics and engineers and enthusiasts to discuss these possibilities in greater detail, examining questions of construction technique and material science and social organization. And these gatherings helped to build a community of believers who took the technical challenges seriously while maintaining optimism about their eventual solutions, a community that would persist in various forms through the decades ahead, even as the broader culture's enthusiasm for space settlement waxed and waned with changing circumstances. The reason that O'Neill and his colleagues focused particularly on the L4 and L5 Lagrange points had to do with the gravitational stability we discussed earlier, those broad stable regions where objects could remain with minimal station-keeping fuel, drifting in slow paths around the mathematical equilibrium point without requiring constant corrective thrust. And this stability meant that large structures parked at L4 or L5 would essentially stay put on their own, maintaining their positions through the natural balance of gravitational forces, which was precisely what you would want for a habitat designed to last for centuries. Beyond stability, the L4 and L5 points offered excellent access to solar energy, lying at the same distance from the Sun as Earth itself, receiving the same intensity of sunlight that powers terrestrial life. And this abundant energy could be collected by vast solar arrays and used to power the habitat systems, to grow their crops under artificial light, and perhaps to beam additional power to Earth or other destinations through microwave transmission, which was another aspect of O'Neill's broader vision for space development as a solution to terrestrial resource constraints. The proximity to lunar materials was also significant, for the Moon lay relatively nearby in orbital terms, and its surface contained useful elements like aluminium and silicon and oxygen that could be extracted and processed and launched into space using mass drivers, electromagnetic catapults that O'Neill believed could accelerate raw materials to escape velocity without chemical rockets, feeding a constant stream of building material to construction facilities at L5 where it could be refined and shaped into habitat components, allowing the colonies to grow using resources from space itself rather than lifting everything expensively from Earth's deep gravity well. The optimism of this period produced timelines that seem rather poignant in retrospect. Predictions that manufacturing facilities might be operating in high orbit by the mid-1980s. That substantial colonies might exist by the end of the century. That millions of people might be living off-world within a generation or two. And while these estimates were not made carelessly, they were made in a particular moment of history when certain trends seemed to promise continued expansion of space capabilities. When energy prices and environmental concerns seemed to create urgent demand for the solutions O'Neill proposed, and when the political will to fund large-scale space projects had not yet dissipated as it would in the decades following. In 1975, a couple named Carolyn and Keith Henson founded an organization called the L5 Society, dedicated to promoting space colonization along the lines O'Neill had described. And this organization adopted a motto that captured the hopeful spirit of the moment with disarming directness, namely L5 in 95, meaning that the Hensons and their fellow members aimed to see a permanent space colony established at the fifth Lagrange point within just 2 decades, a goal that required, in their view, sustained public advocacy and political engagement to ensure that governments would fund the necessary development programs. The L5 Society grew throughout the late 1970s and early 1980s, publishing newsletters and organizing conferences and submitting testimony to Congress, building a grassroots movement of space enthusiasts who kept O'Neill's vision alive, even as NASA's actual activities remained focused on the space shuttle and various scientific missions rather than the ambitious colonization programs that the Society advocated. And this advocacy work helped to maintain a certain constituency for human expansion into space during years when budgetary pressures and shifting priorities might otherwise have allowed the idea to fade entirely from public discourse. By 1987, the L5 Society had decided to merge with another organization called the National Space Institute, which had been founded by the rocket pioneer Wernher von Braun. And this merger produced a new entity called the National Space Society, which continues to exist today as an advocacy organization promoting space exploration and development, carrying forward the work that the Hensons began while addressing a somewhat broader range of space-related causes than the original L5 Society's focused emphasis on high-orbit colonization. Gerard O'Neill himself continued working on space settlement concepts through the 1980s, founding a company called the Space Studies Institute to fund research into enabling technologies, and he remained a thoughtful and articulate spokesman for the possibilities he had outlined, even as the timeline stretched longer and the political environment proved less receptive than he had hoped. And he died in 1992 from leukemia at the age of 65. Leaving behind a body of work that had profoundly influenced how many people thought about the human future in space. The lasting influence of O'Neill's ideas can be traced through various channels, but one of the more significant involves a young Princeton undergraduate named Jeff Bezos, who studied under O'Neill in the late 1980s and developed a deep appreciation for the space habitat concept. An appreciation that Bezos would carry with him through the years of building his online retail company and eventually into his founding of a space venture called Blue Origin, which has stated among its long-term goals the eventual construction of O'Neill-style colonies in high orbit, using technologies that Blue Origin hopes to develop through its launch vehicle and spacecraft programs. In 2019, Bezos gave a presentation that prominently featured artwork depicting O'Neill cylinders, showing verdant landscapes curving upward into the distance, showing cities and farmland and forests all contained within vast rotating structures. And while the timelines Bezos suggested were considerably longer than those the L5 Society once proposed, the basic vision remained recognizable from O'Neill's original papers and books. A vision of humanity spreading through the solar system not by clinging to planetary surfaces but by building new worlds from raw materials, harvesting energy from the sun, and making homes in the gravitationally stable regions where the orbital mechanics favor long-term settlement. And so O'Neill's dream persists, carried forward by organizations and individuals and companies that trace their inspiration back to those Princeton seminars and Physics Today papers and the slim hopeful volume of The High Frontier, waiting for the moment when technologies and economics and political will might finally align to begin the long process of construction, of launching materials and assembling structures and inviting the first permanent residents to take up life in the cosmic parking spots that Lagrange discovered mathematically and O'Neill reimagined as harbors for human civilization, places where gravity balances and sunlight streams, and the future waits patiently for those who might one day arrive. So far we have been speaking of the Lagrange points that exist between our Earth and the Sun, those distant gravitational harbors situated roughly 1.5 million kilometers from our planet, where spacecraft like the James Webb Space Telescope drift in their gentle halo orbits while observing the universe. But it is worth remembering, as you settle deeper into your pillow and let your breathing grow slow and even, that Lagrange points are not unique to the Earth-Sun system at all. They emerge wherever two massive bodies orbit one another, creating those 5 special locations where the gravitational forces arrange themselves into something approaching equilibrium. And so there exists another set of 5 Lagrange points, much closer to home, formed by the gravitational relationship between the Earth and our own familiar Moon. These Earth-Moon Lagrange points are considerably nearer to us than their Sun-Earth cousins, and they have their own particular characteristics, their own gentle orbital behaviors, and their own growing importance for the future of space exploration, particularly as humanity turns its attention once more toward our ancient companion in the sky. The Earth-Moon L1 point, for instance, lies along the line connecting the centers of the Earth and the Moon, positioned at a distance of approximately 58,000 kilometers from the lunar surface. This is remarkably close when compared to the vast distances we have been discussing in relation to the Sun-Earth points, and it means that spacecraft stationed near Earth-Moon L1 can serve as useful waypoints for missions traveling between our planet and the Moon. The journey from low Earth orbit to the Earth-Moon L1 point requires considerably less energy than the journey all the way to the lunar surface, and so this location has long been considered a potential staging area, a place where spacecraft might pause, refuel, or transfer cargo before continuing on to their final destination. Some proposals have suggested that materials mined from the lunar surface, perhaps water ice from the permanently shadowed craters near the poles, or metals extracted from the regolith, could be transported to a station at Earth-Moon L1 and from there distributed to other destinations with relative ease. The gravitational arithmetic of such a way station is rather elegant, for objects at L1 require only modest amounts of energy to be nudged either moonward or earthward, making it a kind of cosmic crossroads where resources might be exchanged between the two worlds. But it is the Earth-Moon L2 point that has attracted perhaps the most interest in recent years, and it is here that we shall linger for a while as the night grows quieter and your thoughts drift gently toward sleep. The Earth-Moon L2 point lies beyond the Moon as seen from Earth, positioned along that same Earth-Moon line but on the far side of our satellite, at a distance of roughly 64,000 kilometers beyond the lunar surface. This location is hidden from Earth by the bulk of the Moon itself, which might seem at first to be a disadvantage, but it is precisely this geometry that makes Earth-Moon L2 so valuable for a very particular purpose. You see, the far side of the Moon, that hemisphere which perpetually faces away from Earth due to the Moon's tidally locked rotation, has long presented a challenge for spacecraft and missions seeking to explore it. Any lander or rover placed upon the lunar far side cannot communicate directly with Earth, for the Moon's rocky body blocks all radio signals, creating a zone of permanent radio silence that stretches across nearly an entire hemisphere of the lunar surface. For most of the space age, this communication barrier made far-side missions extremely difficult to conduct, and so the far side remained largely unexplored, a quiet and cratered wilderness known only through orbital photography. The solution to this communication problem was recognized quite early in the history of space exploration, and here we might pause to acknowledge the remarkable foresight of Arthur C. Clarke, the British author and inventor who is perhaps best known for his science fiction novels, but who also made significant contributions to the practical understanding of satellite communications. In 1950, many years before any spacecraft had left the Earth, Clarke proposed the idea of placing a relay satellite at the Earth-Moon L2 point, where it would hover perpetually beyond the far side of the Moon and serve as a communications bridge between Earth and any future explorers on that hidden hemisphere. Clarke understood that a satellite at L2 would maintain a constant geometric relationship with both the Earth and the Moon, always remaining in a position where it could see both the far side lunar surface and the distant Earth, thereby providing an unbroken radio link across what would otherwise be an impassable barrier. It was a typically elegant solution from a mind that seemed to delight in finding practical applications for orbital mechanics, and though it would take nearly 7 decades for Clarke's vision to become reality, his proposal demonstrated how the Lagrange points might serve not merely as scientific curiosities but as genuinely useful locations for the infrastructure of space exploration. The first spacecraft to take up residence in a halo orbit around the Earth-Moon L2 point was a Chinese relay satellite named Quqiao, a name which translates from Mandarin as Magpie Bridge, referring to a beautiful legend in Chinese folklore about a bridge of magpies that forms across the heavens to allow two separated lovers to meet once each year. Quqiao was launched in May of 2018 and carefully maneuvered into a halo orbit around the Earth-Moon L2 point, where it began its patient work of listening and relaying. The orbit that Quqiao follows is not a simple circle or ellipse around the L2 point itself, but rather a large looping halo orbit that takes the satellite on a gentle path around the point, sometimes as far as 80,000 kilometers from the L2 location, ensuring that it always maintains a clear line of sight to both Earth and the far side of the Moon. This orbital arrangement allows Quqiao to serve as a constant communications link, receiving signals from the lunar surface and retransmitting them toward Earth, and receiving commands from Earth to pass along to the spacecraft below. The purpose of Quqiao became clear in January of 2019, when China's Chang'e 4 mission achieved the first ever soft landing on the far side of the Moon, setting down in the von Karman crater within the vast South Pole Aitken Basin. The lander and its small rover, named U-22 or Jade Rabbit 2, have been exploring this ancient and scientifically fascinating terrain ever since, studying the composition of the lunar soil, measuring radiation levels, and even attempting to grow plants in a small sealed biosphere. None of this would have been possible without Quqiao drifting quietly at its station beyond the Moon, catching every transmission from the surface and sending it home across the void, a magpie bridge of radio waves spanning the silence between worlds. The success of this relay architecture has encouraged China to plan further infrastructure at the Earth-Moon L2 point, with proposals for additional communication satellites that would create a more robust network capable of supporting multiple far-side missions simultaneously. In this way, the Earth-Moon L2 point is gradually becoming a kind of communications hub, a permanent installation in the architecture of lunar exploration. The orbital dynamics of the Earth-Moon Lagrange points differ in some important ways from those of the Sun-Earth points, and these differences are worth understanding even if the mathematics themselves need not concern us as we rest. The Moon's orbit around Earth is not perfectly circular but rather slightly elliptical, which means that the distance between Earth and Moon varies somewhat over the course of each lunar month. This eccentricity causes the positions of the Lagrange points to shift slightly as the Moon moves closer to and farther from the Earth, introducing a gentle oscillation into what might otherwise be fixed locations. Additionally, the Sun exerts its own gravitational influence on the Earth-Moon system, creating perturbations that tug at any spacecraft stationed near the Lagrange points and gradually alter their orbits over time. These solar perturbations are proportionally more significant for the Earth-Moon points than for the Sun-Earth points, because the Earth-Moon system is so much smaller and the Sun's relative influence correspondingly greater. The result is that maintaining a stable orbit near the Earth-Moon L2 point requires somewhat more frequent station-keeping maneuvers, small adjustments using onboard thrusters to counteract the accumulated effects of these perturbations. QQIAO carries fuel for these maneuvers and has demonstrated that such orbits can be maintained over extended periods with proper planning and care. As you lie there in the comfortable darkness, breathing slowly and evenly, it may be pleasant to consider that the Moon's far side, once the most isolated and silent place accessible to human exploration, is now connected to us by this delicate chain of radio signals passing through a Chinese satellite named after a bridge of birds. The poetry of it is rather lovely, in its quiet way. Looking forward, the Earth-Moon Lagrange points figure prominently in the plans of several space agencies for the coming decades. Perhaps the most ambitious of these plans involves the Lunar Gateway, a small space station that NASA and its international partners intend to construct in orbit around the Moon as part of the Artemis program. The Gateway will not occupy a halo orbit directly around one of the Lagrange points, but will instead follow what is called a near-rectilinear halo orbit, a highly elongated path that takes the station close to the Moon at its nearest point, passing within 3,000 kilometers of the lunar surface, and then swinging far out into space at its most distant point, reaching distances of 70,000 kilometers or more. This unusual orbit passes near both the Earth-Moon L1 and L2 points during different portions of its roughly week-long period, taking advantage of the gravitational characteristics of these regions, while also providing excellent access to the lunar surface for crewed landing missions. The orbit is particularly efficient in terms of fuel consumption, requiring only small amounts of propellant to maintain, and it offers continuous communication with Earth for most of its duration. Before committing to this orbit for the Gateway, NASA launched a small Pathfinder mission called Capstone, which stands for Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment. Capstone is a tiny spacecraft, what is sometimes called a CubeSat, weighing only about 25 kilograms, and it was launched in June of 2022 on a long, fuel-efficient trajectory toward the Moon. After a journey of several months, Capstone entered the near-rectilinear halo orbit that the Gateway will eventually occupy, becoming the first spacecraft to test this particular orbital path. The mission has been gathering data on the orbital dynamics, testing navigation techniques, and demonstrating that the orbit is indeed stable and practical for long-duration occupation. This sort of careful preparatory work, sending small inexpensive missions to test conditions before committing larger resources, is characteristic of thoughtful space exploration, and Capstone's quiet success has helped to confirm that the Gateway's planned orbit is suitable for its intended purpose. Russia, too, has expressed interest in the Earth-Moon Lagrange points as part of its lunar exploration program. The planned Luna 26 mission, an orbiter intended to study the Moon from space, may make use of orbits that pass near these gravitational balance points, though the specific details of its trajectory have varied in different planning documents over the years. The lunar program has a long and storied history stretching back to the earliest days of the space age, and Luna 26, if and when it flies, would continue this tradition of careful scientific investigation of our nearest celestial neighbor. Other nations and space agencies have their own plans for the cislunar region, that sphere of space encompassing the Earth-Moon system, and the Lagrange points will likely play an increasingly important role in the architecture of stations, relays, and waypoints that may one day make travel between Earth and Moon a routine matter. For now, these Earth-Moon Lagrange points remain quiet places, visited only occasionally by spacecraft on their way to somewhere else, or occupied by a single relay satellite maintaining its patient vigil beyond the Moon. But the infrastructure is beginning to take shape, piece by piece, and in the coming decades these gravitational balance points may become as familiar to mission planners as any location in low Earth orbit. The distances are modest by cosmic standards, a few 100,000 kilometers at most, close enough that signals travel between Earth and the Lagrange points in little more than a second, close enough that spacecraft can reach them in a matter of days rather than months. And yet they occupy positions of genuine strategic and scientific importance, places where the invisible architecture of gravity creates natural harbors for human machines. Arthur C. Clarke understood this in 1950, imagining relay stations that would not be built for nearly 70 years. Kukiao now floats where he envisioned, carrying signals from the hidden face of the Moon, and the Gateway will soon join it in those quiet regions where the gravitational tides run slow and gentle. And so we come to consider what lies ahead, which is to say, the many ways in which these peculiar gravitational sweet spots may serve humanity's ventures beyond our world in the decades and perhaps centuries to come. The Lagrange points, having proved themselves useful for astronomical observatories and solar monitors, are now being contemplated for purposes far more ambitious, purposes that extend well beyond the placement of telescopes and into the realm of infrastructure, of waypoints, of the kind of permanent installations that might one day make travel through the inner solar system something approaching routine. These are not fanciful notions, but rather the subject of serious engineering studies and mission proposals, the sort of detailed planning that space agencies undertake when they believe something is genuinely achievable within a reasonable time frame. Let us begin with perhaps the most practical near-term application, which concerns the Earth-Moon Lagrange point known as L1, positioned between our planet and its companion world. This location has attracted considerable interest as a potential site for what mission planners sometimes call a fuel depot, though the reality would be rather more sophisticated than that modest term suggests. The concept involves establishing a facility at Earth-Moon L1 where spacecraft bound for Mars or other distant destinations could refuel and resupply before continuing their journeys. The advantages of such an arrangement stem from the basic economics of spaceflight, in which the most expensive portion of any mission, measured in terms of energy expenditure, is the initial climb out of Earth's deep gravity well. A vehicle that departs from low Earth orbit carrying only enough fuel to reach L1, where it then takes on additional propellant, can ultimately deliver far more payload to Mars than one that must carry all its fuel from a surface. The fuel itself might eventually come from lunar sources, water ice from the Moon's polar regions processed into hydrogen and oxygen, though in the nearer term it would likely be launched from Earth and stored at the depot. The gravitational stability of L1, while imperfect and requiring occasional station keeping, is entirely adequate for such purposes, and the location serves as a kind of crossroads from which both lunar and interplanetary destinations become more readily accessible. The extraction and processing of resources from asteroids, a concept that has moved gradually from science fiction into serious economic analysis, might similarly benefit from Lagrange point infrastructure. The Sun-Earth L1 and L2 points have been proposed as locations for processing stations where material retrieved from near-Earth asteroids could be refined and prepared for use. An asteroid mining vessel, having rendezvoused with its target and extracted valuable ores, would face the challenge of returning those materials to where they might actually be used. Bringing raw asteroid material all the way down to Earth's surface is energetically wasteful and potentially hazardous, but delivering it to a processing facility at L1 or L2 represents a far more elegant solution. At such a station, metals could be smelted, water could be purified and electrolyzed into propellant, and various industrial processes could be conducted in the benign microgravity environment, all without the complications of atmospheric interference or the expense of repeated descents and ascents through planetary gravity wells. The refined products might then be shipped to wherever they were needed, to orbital construction facilities, to the lunar surface, to Mars-bound vessels, or in some cases down to Earth. These remain, for the moment, concepts rather than concrete plans, but they represent the kind of systematic thinking about space infrastructure that Lagrange points naturally invite. The European Space Agency has been developing a mission called Vigil, formerly known by the more descriptive name Lagrange, which would place a spacecraft at the Sun-Earth L5 point for the purpose of monitoring space weather. This location, trailing 60 degrees behind Earth in its orbit, provides an ideal vantage point from which to observe the Sun's surface before it rotates to face our planet. Solar storms that might affect Earth, producing the coronal mass ejections that can disrupt power grids and satellite operations, typically become visible from L5 several days before they would be apparent from Earth or from spacecraft positioned along the Sun-Earth line. Vigil would serve as an early warning system, providing crucial advance notice that would allow satellite operators to take protective measures and power grid managers to prepare for potential disruptions. The mission represents a recognition that space weather has become a matter of practical economic concern, not merely scientific interest, and that the L5 vantage point offers capabilities that cannot be replicated from any other location. In a similar vein, the American Space Agency has been preparing a mission called NEO Surveyor, designed to detect and catalog asteroids that might pose a hazard to Earth. This spacecraft is intended to operate from the Sun-Earth L1 point, from which it can survey the inner solar system with infrared instruments capable of detecting the faint thermal signatures of rocky bodies against the cold background of space. The L1 location is particularly suitable for this purpose because it allows the spacecraft to look outward from the Sun, observing the region of space through which near-Earth asteroids pass, while remaining in a stable thermal environment conducive to sensitive infrared observations. The mission addresses a practical concern: the possibility that an undetected asteroid might one day approach on a collision course, and L1 provides the observational geometry necessary to conduct a comprehensive survey of objects that might otherwise remain hidden in the Sun's glare. The notion of communication infrastructure at Lagrange points extends beyond individual missions to encompass something rather more ambitious, which some have termed an interplanetary internet. As humanity's presence in space expands, with missions to the Moon, to Mars, and eventually to more distant destinations, the challenge of maintaining reliable communication becomes increasingly complex. Lagrange points offer natural locations for relay stations that could store and forward data across the solar system, taking advantage of their gravitational stability to maintain permanent communication nodes without continuous propulsive effort. A network of such stations, positioned at various Lagrange points throughout the inner solar system, could provide redundant pathways for data transmission, ensuring that contact with distant spacecraft and settlements is maintained even when direct line-of-sight communication is blocked by the Sun or other bodies. The Mars-Sun Lagrange points, particularly L4 and L5, have been specifically proposed as locations for communication relays that would maintain contact with Mars during the periods when the Sun lies directly between the two planets, a circumstance that currently interrupts communication for several weeks during each Martian year. Among the more speculative proposals that nonetheless rest on sound physical principles is the concept of a solar gravitational lens mission, which would exploit the way in which the Sun's mass bends light to create a natural telescope of extraordinary power. At a distance of approximately 550 astronomical units from the Sun, light from distant objects is focused by solar gravity to a point where it could be collected by a spacecraft, potentially enabling the direct imaging of exoplanets around nearby stars at resolutions far exceeding anything achievable through conventional means. Such a mission would require travel to a distance roughly 14 times farther than Voyager 1 has ventured, a journey of decades even with advanced propulsion systems. Mission planners contemplating this extraordinary voyage have noted that the Sun-Earth L2 point would serve as a logical departure point, a location from which a spacecraft could be accelerated outward with maximum efficiency, taking advantage of the gravitational and orbital dynamics that make L2 a natural gateway to the outer solar system. The mission remains in the realm of advanced concept studies, but it illustrates how Lagrange points might serve not merely as destinations but as waypoints on journeys to far more distant shores. The Breakthrough Starshot initiative, which aims to send small spacecraft to nearby star systems using powerful ground-based or space-based lasers for propulsion, has considered L2 as a potential location for its laser array. Positioning such an array at L2 would avoid many of the complications associated with ground-based operation, including atmospheric distortion and the need to track targets across a rotating sky, while providing a stable platform from which to direct concentrated laser light at the tiny spacecraft accelerating toward interstellar space. The engineering challenges remain formidable, but the basic concept of using a Lagrange point as a platform for propelling spacecraft to other stars represents perhaps the most ambitious application yet proposed for these gravitational waypoints. The revival of interest in large-scale space habitation has brought renewed attention to concepts first articulated decades ago by the physicist Gerard O'Neill, who envisioned permanent human settlements at the Earth-Moon L4 and L5 points. Modern versions of these proposals take advantage of advances in material science, robotics, and manufacturing technology that were not available in O'Neill's time, and they incorporate the possibility of using lunar and asteroidal resources rather than lifting everything from Earth's surface. The gravitational stability of L4 and L5, which we have discussed at some length in earlier portions of this account, makes them particularly attractive for such settlements, as they would require minimal propulsion to maintain their positions over indefinite timescales. The manufacturing advantages of operating at gravitationally stable points extend beyond mere convenience to include the possibility of producing materials and structures that would be impossible to create under the influence of planetary gravity. Certain crystalline substances, extremely pure metal alloys, and structures of such size and delicacy that they could not withstand their own weight on any planetary surface. The Chinese space program has announced intentions to place a spacecraft at the Sun-Earth L5 point for solar observation, joining the growing international presence at Lagrange points and demonstrating the global recognition of these locations' scientific and practical value. This mission would complement observations from other vantage points, contributing to the worldwide effort to understand and predict solar activity. A particularly interesting mission currently in progress is the European Space Agency's Comet Interceptor, which was launched in 2024 and is currently stationed at the Sun-Earth L2 point awaiting the discovery of a suitable target. Unlike conventional missions, which are designed around specific known objects, Comet Interceptor takes advantage of L2's utility as a waiting position from which a rapid response can be mounted. The spacecraft will remain at L2 until astronomers discover a suitable long-period comet or interstellar object making its first approach to the inner solar system, at which point it will depart to intercept the visitor. This approach would be impractical without L2's stable environment, and it represents a new paradigm in which spacecraft can be prepositioned and held in reserve for targets that have not yet been identified. India's Space Research Organisation has maintained its presence at the Sun-Earth L1 point with the Aditya mission, joining the international community of nations operating spacecraft at Lagrange points. This continued Indian presence, alongside European, American, and Chinese missions, signals the broad global interest in these locations and the recognition that access to Lagrange points is becoming an essential capability for any nation with serious spacefaring ambitions. As you rest there, breathing gently, you might let your thoughts drift across these possibilities without urgency or concern, simply noting that the same gravitational mathematics that holds telescopes in their positions today may one day support fuel depots and manufacturing facilities, communication relays, and departure platforms for journeys we can scarcely imagine. The Lagrange points will be there when humanity is ready for them, patient and unchanging, governed by the same principles that Euler and Lagrange worked out with quill pens and candlelight. And now, knowing something of what may come, you can let your eyes grow heavy and your thoughts grow dim, secure in the knowledge that the cosmos keeps its own counsel and its own time, and that all these ambitious plans will unfold, if they unfold at all, at the measured pace of careful engineering and patient observation, long after you have drifted off into well-deserved sleep.